Hello there, and welcome to Just About Earth, where curiosity settles in softly, and the mysteries of our planet drift through the quiet like snowflakes in the night. Tonight's story is a little colder than usual, but perhaps just as comforting. It's about a time when the world you know, with its forests and cities and sunlit seas, looked utterly different. There were no trees, no animals, not even green continents, just ice. Endless, gleaming, unbroken ice. Imagine the whole planet wearing a white coat so thick it turned even the equator into a frozen desert. That was Earth once, during a period scientists call the Cryogenian, when our home may have become the biggest snowball in the solar system. Before we set off into that frozen world, I wonder, what's the temperature where you are right now? Is it warm where you're listening, or can you feel a bit of winter in the air? Maybe it's night and you're wrapped in a blanket, or morning with steam rising from a mug nearby. Either way, thank you for joining me here, for taking this quiet moment to look not out a window, but far back in time, to an age so long ago that the moon looked the same, but everything beneath it did not. If you find comfort in these soft wanderings through science and story, it would mean the world if you left a like, or subscribed, or shared this calm little space with someone who might enjoy learning before sleep. It helps more than you'd think. Now take a slow breath, let your mind settle, and picture the world as it once was. Not blue and green, but white and silver and silent. The Earth of that distant age was more than 600 million years removed from the one outside your window tonight. Continents were clustered differently, drifting slowly across a planet that had long since cooled from its fiery youth. Volcanoes still breathed fire, but life had not yet ventured beyond the oceans. What little lived then was microscopic, simple, resilient, mostly unseen. If you could have stood on land and somehow survived the cold, you would have seen no plants, no grass, only bare rock, and the glitter of ice sheets stretching toward a horizon that looked almost metallic beneath the dim sun. The sky might have held a faint bluish haze thinner than ours, because oxygen was still scarce. There was carbon dioxide, methane, nitrogen, and the faint ghost of water vapour freezing into delicate clouds that barely moved in the still air. This wasn't how Earth had always been. For billions of years before the Cryogenian, the planet had been warmer, sometimes oppressively so. The young sun, though dimmer than today, had been balanced by thick greenhouse gases that trapped enough heat to keep the oceans liquid. Stromatolites, layered mounds built by colonies of microbes, thrived in shallow waters. They were among the first great builders of ecosystems, long before plants or animals appeared, but even their slow, simple activity changed the atmosphere. Over eons they exhaled oxygen as waste, gradually stripping the air of carbon dioxide. Volcanoes replenished some of it, but the balance shifted. When the continents began to move, new mountains rose, rocks weathered, and more carbon dioxide was drawn out of the sky through chemical reactions with rain and minerals. Slowly, imperceptibly, the blanket that kept the planet warm began to thin. It didn't happen overnight. It might have taken millions of years for the tipping point to arrive. A chain of small changes that led to one of the greatest transformations in Earth's history. Scientists think it began when the supercontinent Rodinia started to break apart. The splitting of land opened new coastlines, where rainfall and erosion could pull even more carbon from the air. Meanwhile, the distribution of continents closer to the equator meant that bright ice could form there more easily, reflecting sunlight back into space. That reflection, called albedo, is powerful. The more light that bounces away, the cooler the planet becomes. The cooler it gets, the more ice spreads, which reflects even more light, and so the spiral continues. It's a feedback loop, one that doesn't stop until something else interrupts it. At first, the cold might have been regional. Glaciers advancing from the poles, seasonal snow lingering longer each year, but eventually it crossed a threshold. The oceans began to freeze, The line of frost crept outward until even tropical waters were capped by thick ice. Beneath the frozen surface there may have been pockets of brine where simple organisms continued their slow dance of survival, feeding on the faint chemical energy that seeped up from the seafloor. Above them, the surface turned into a mirror so bright that sunlight struggled to penetrate. It's strange to think of Earth like that, not blue and full of motion, but pale and still. From space, it would have been dazzling, almost too bright to look at. A white marble in the dark, shining against the velvet of the cosmos. The clouds that once drifted lazily would have vanished, replaced by a high, thin mist of ice crystals. The atmosphere itself may have been quiet, with winds diminished by the lack of heat differences between regions. Even the usual hum of the planet, rain, waves, storms, would have been subdued. For life, such conditions were catastrophic, but not entirely fatal. The earliest microbes had already adapted to extremes long before. Some may have found refuge in cracks within the ice, where faint light could still reach and melt small channels of liquid water. Others could have survived near volcanic vents, feeding on chemical gradients where the crust met the ocean. The story of life on Earth, as it turns out, is not just one of flourishing, but of endurance. The evidence for this ancient freeze lies hidden in rocks that were once seabeds. Geologists have found layers of glacial debris, drop stones, boulders carried by ice and dropped into soft sediment, in places that were near the equator at the time. These stones, frozen into ancient mud, tell of icebergs drifting across oceans that should have been warm. Their presence so far from the poles was the first clue that the Cryogenian was not just another ice age, but something far more dramatic. It took decades for scientists to piece together the clues. At first, the idea that the whole planet could freeze seemed absurd. After all, how could life survive? How could the cycle of carbon and water continue if everything were locked in ice? But more evidence emerged. Chemical signatures in ancient rocks showing sudden changes in carbon isotopes, marks of a planet struggling to breathe. These signatures, found on every continent, point to global events rather than local ones. The conclusion, though still debated in detail, is clear enough. The world nearly froze to death. Imagine what it might have felt like to witness the beginning of that transformation. The seas, once dark and restless, gradually calming as ice spread across their surfaces, the light dimming, not from clouds but from the sheer whiteness of the earth reflecting the sun away. Each year colder than the last, the horizon creeping closer as snow buried everything in sight, rivers solidifying into ribbons of glass, mountains crowned in ice that never melted. Perhaps the last patches of open water steamed faintly in the cold air before sealing shut. A hush would have fallen over the world, not the silence of peace, but the silence of exhaustion. Yet even in that stillness, something extraordinary was happening. The planet wasn't dead. Beneath kilometres of ice, geothermal heat continued to rise from the mantle. Volcanic islands still erupted here and there, releasing gases that could not easily escape the frozen air. Over millions of years, those gases, carbon dioxide above all, began to build up. Slowly, the invisible breath of volcanoes started to thicken the atmosphere again. But for now, in this frozen dawn, that warmth was only a promise. The Cryogenian Period is divided into two main glaciations, the Sturtian and the Marinoan. Each may have lasted tens of millions of years. Between them, there might have been brief thaws, but the world never fully recovered until the very end. To put that in perspective, the last ice age that shaped human evolution lasted less than 3 million years, and its coldest stages only tens of thousands. The Cryogenian's reign of ice was on a scale almost beyond imagination. The air would have been thin and dry, the ocean surface sealed, the sun a weak disk in a pale sky. The contrast between heat beneath the crust and cold above it could have produced strange phenomena, subglacial lakes, frozen geysers, even pockets of supercooled brine where life found improbable shelter. Some scientists think these hidden environments were crucial. They may have preserved lineages of photosynthetic organisms that, once the thaw came, exploded in diversity. All of this began from a few small changes in how the planet breathed. It's humbling to think that a slightly different tilt, a shift in landmass, or a slow drawdown of carbon dioxide could transform an entire world. But that's the story of Earth. It has always been sensitive, reactive, and capable of reinventing itself. The ice that wrapped the planet was not punishment, not a final chapter, but part of a long dialogue between rock, air, ocean, and life. If you picture the Earth as a living organism, the Cryogenian was like a long, deep sleep. The heartbeat slowed, the metabolism quieted, but the potential remained. Underneath the frost, chemistry continued. Nutrients accumulated, gases shifted, and the stage was being quietly set for something remarkable to follow. The deep freeze would eventually give way to warmth, and with it, new forms of life that would shape everything to come. For now, though, we remain in that frozen silence, with ice covering continents and oceans alike. The stars above look down on a planet unrecognizable yet still familiar in its bones. The continents rested where they drifted, the magnetic poles wandered, and the air held its breath. In that hush, the story of life persisted, waiting for the warmth that would one day return. And that's where we'll stay for the moment, here in the quiet, before the ice began its slow, inevitable spread. In the next part of our journey, we'll drift back a little further to see what the world was like before it began to freeze, when seas shimmered and the first whispers of change stirred beneath the waves, setting in motion the chain of events that would wrap the planet in white. Before the world turned white, it was alive in a very different way, not with forests or animals or anything familiar to the eye, but with movement and colour at scales too small to see. The oceans were dark and greenish, filled with microscopic life forms drifting in the currents. They were simple but tenacious, the quiet architects of the planet's chemistry. For billions of years, these tiny organisms had shaped the air, the water and the minerals beneath. They had no bones, no shells, no eyes, but they were the reason the sky was slowly turning blue and the seas were growing richer with the ingredients of future life. If you could have stood on a rocky shore in that time, more than 700 million years ago, you might not have recognized the Earth as home. The continents were arranged differently, gathered together in a supercontinent that geologists later named Rodinia. It stretched like an uneven ring across the equator, surrounded by a vast ocean known as Morovia. The air would have felt thin and raw, carrying a faint sharpness from volcanic gases. There was no grass beneath your feet, only rough stone, sand, and the occasional film of microbes forming a slippery layer where moisture lingered. The colours of the world were muted: grey rock, dark blue water, rusty streaks of iron, and the pale glare of a younger sun shining through a hazy atmosphere. The sun itself was dimmer than the one we know. Astronomers estimate that it emitted roughly 6% less energy than it does today. That might not sound like much, but over the vastness of a planet's surface it made a difference. To keep warm, the Earth relied heavily on its greenhouse gases, chiefly carbon dioxide and methane. These gases trapped heat radiating from the surface, maintaining a climate that allowed liquid water to exist despite the faint sunlight. It was a delicate balance, one that had held for billions of years. But balance on a planetary scale is rarely permanent. Volcanoes dotted the land, releasing gases that both warmed and nourished the atmosphere. When lava met seawater, it hissed and cracked, creating steam and minerals that rained back into the ocean. Over time, this constant exchange between land, sea and air built up the complex system we now call the carbon cycle. Carbon dioxide would enter the air through volcanic activity, dissolve into the oceans, combine with calcium to form carbonates, and eventually become locked away in stone. Through this endless cycle, Earth regulated its own temperature like a living organism adjusting its breath. But sometimes, it overcompensated. In the eons before the Cryogenian, the balance began to tip. The continents, pulled slowly by the invisible churn of the mantle below, drifted across the surface. As Rodinia broke apart, new coastlines formed, exposing fresh rock to weathering. Rain fell on these rocks, dissolving minerals that captured carbon dioxide and washed it into the sea. The more land exposed, the more carbon was drawn out of the atmosphere, and the thinner Earth's insulating blanket became. At the same time, the appearance of new oceanic ridges and seafloor activity changed the distribution of heat across the globe. The combination was subtle, but powerful, a recipe for cooling that would take millions of years to unfold. In the shallows near these young coastlines, microbial life thrived. Cyanobacteria, among the earliest photosynthetic organisms, absorbed sunlight and released oxygen. Their activity was slow but relentless, and over vast stretches of time they changed the chemistry of the planet. What had once been a world rich in carbon dioxide was gradually becoming more oxidized. Iron that once floated freely in the oceans began to rust, settling out as bands of red in the rocks we can still see today. The oceans grew clearer, the sky brighter, but the air cooler. It's hard to imagine a planet where life reshapes the climate without intending to, yet that's what was happening. The very organisms that depended on warmth and water were, by their own success, creating conditions that would soon threaten them. By consuming carbon dioxide and releasing oxygen, they reduced the greenhouse effect that had kept the planet comfortable. With less carbon dioxide to trap heat, the Earth began to lose warmth to space faster than it could replenish it. The continents themselves were positioned in a way that made things worse. Much of Rodinia lay near the equator, where sunlight is strongest. When ice began to form, even in small patches it reflected more sunlight away, creating a local cooling effect. Normally ice forms at the poles, but when it appears in the tropics the effect is far more dramatic. The reflective surface sends vast amounts of energy back into space, and the surrounding air cools rapidly. Once that process began, it was difficult to stop. But before that runaway freeze, the world was still dynamic and full of motion. Winds whipped across the open ocean, storms gathered and broke, and waves rolled endlessly against bare shores. Rivers cut through valleys, carrying minerals to the sea. Lightning flashed across skies rich in nitrogen and oxygen, driving the chemistry that produced nitrates, compounds essential for life. The Earth was not quiet then. It was restless, vibrant, a place of constant transformation. In the oceans, microscopic algae and bacteria formed floating mats that drifted with the currents. These organisms captured sunlight through photosynthesis, releasing bubbles of oxygen that rose to the surface and escaped into the air. Deeper down, where light could not reach, other microbes fed on sulfur and iron, drawing energy from chemical reactions instead of the sun. This interplay of photosynthetic and chemosynthetic life created a patchwork of ecosystems, unlike anything on the modern planet. The water itself would have been darker and murkier than today's seas. High levels of dissolved iron and other minerals tinted it a deep greenish blue. Waves would have carried a metallic sheen, and near volcanic regions, plumes of steam and ash coloured the horizon. At night, without vegetation or city lights, the sky would have been brilliant. The Milky Way stretched sharply across the darkness, unfiltered by pollution or moisture. Meteor showers may have appeared brighter, their streaks reflecting faintly in the ocean below. It was, in its own way, a beautiful world, harsh but alive, raw but full of potential. Temperatures varied across the planet, but overall it was cooling. Ice began to appear at high latitudes, creeping down from the poles during long winters. Glaciers carved valleys, leaving behind fine sediments that washed into the sea. In some regions, snow lingered year-round, building layer upon layer. Yet for millions of years, the system held on the edge of balance. There were still warm seasons, still open water, still life thriving in the shallows. But the signs of instability were there. scientists studying ancient rocks have found evidence that the climate was becoming increasingly erratic in the run-up to the Cryogenian glaciations. Isotopic records suggest large swings in carbon levels, hinting at disruptions in the carbon cycle. It's as if the planet were breathing unevenly, sometimes exhaling more carbon dioxide through volcanic activity, other times inhaling too much through weathering and biological processes. These fluctuations might have caused periods of warming and cooling that eventually tipped the scales toward the deep freeze. Even the magnetic record of the rocks tells part of the story. By studying the orientation of magnetic minerals, geologists can determine where the continents were relative to the poles at different times. The data shows that during the late Proterozoic era, large land masses sat near the equator. This placement meant that when ice began to grow there, it reflected far more sunlight than if it had formed at higher latitudes. The planet's geography itself was conspiring toward cold. Still, it's worth remembering that the Earth of this time was not lifeless. The biosphere, though limited to simple forms, was resilient. Stromatolites continued to grow in shallow seas, their layered domes recording the rhythms of sunlight and tides. In deeper water, plankton-like organisms floated freely, dividing and drifting in endless cycles. Some may have evolved into more complex cells, eukaryotes, with internal structures that hinted at the possibilities to come. The Cryogenians' freeze would later test them to the limit, but before that, they enjoyed a long age of quiet expansion. On land, the picture was stark but not empty. The rocky surfaces may have been coated in microbial films that trapped dust and moisture, forming a thin biological crust. These early terrestrial communities helped stabilize soil and influenced the chemistry of the atmosphere. They were the faint beginning of life's conquest of the continents, though true land plants would not appear for hundreds of millions of years more. Volcanic eruptions were a constant presence, shaping the landscape and renewing the supply of carbon dioxide. Some eruptions were vast, covering entire regions with basalt flows that glowed for years before cooling. When these flows met water, they released gases and minerals that fed marine life. Iron, in particular, was abundant, and its interaction with oxygen produced striking colours, reds, browns and purples that stained the seabed. Even in a world without flowers or coral reefs, there was colour, though it came from chemistry rather than biology. The climate system was sensitive, and as cooling intensified, feedback mechanisms began to reinforce it. With less carbon dioxide, plants could not compensate because they did not yet exist. Oceans absorbed even more heat as they cooled, making it harder to reverse the trend. Snowfall increased, covering land that reflected sunlight more efficiently than bare rock. The threshold was approaching, and once crossed, the transformation would be swift by geological standards. Scientists have tried to model what that transition might have looked like. Some estimate that once ice reached within about 30 degrees of the equator, the planet's albedo would have risen enough to trigger runaway cooling. Temperatures might have fallen rapidly, dropping the average global temperature by dozens of degrees Celsius. The seas began to freeze from the top down, and within a few thousand years, a blink in geological time, the world was locked in ice. But before that tipping point, there was a long twilight period, a time of uneasy balance when the planet teetered between warmth and cold, life and stillness. That twilight world was filled with contrasts. In some regions, rainstorms still lashed the coastlines, while others lay under frost. The air may have carried both the scent of wet minerals and the faint sharpness of snow. Lightning storms illuminated the sky over dark seas, feeding nitrogen into the biosphere. In the oceans, microbial colonies drifted and multiplied, unaware that they were living at the edge of a catastrophe that would test every form of life on Earth. When scientists look back through time using isotopes, rocks and fossils, they see this period as a long prelude, a slow tightening of conditions that would culminate in the Cryogenians' frozen grip. Yet within that prelude lay the seeds of survival. Life adapted in small ways that would later prove essential. Some microbes learned to tolerate saltier conditions as the oceans evaporated in cold, dry air. Others evolved ways to endure low light, preparing them unknowingly for the dim world beneath ice. The stage was being set for one of the most extraordinary recoveries in planetary history. The world before the freeze was not merely a warmer version of what came after. It was a planet on the cusp of transformation, one whose chemistry and geography had aligned to produce both disaster and opportunity. It was a restless world, full of unseen motion, winds, currents, tectonic shifts, and biological whispers. Everything that would define the next great chapter of Earth's story was already in motion, even if no living thing could sense it. As temperatures continued their long descent and glaciers crept closer to the equator, the subtle rhythms of this ancient world began to falter. The ocean currents slowed, the weather grew strange, and the line between seasons blurred. It must have been both gradual and sudden, a million years of cooling punctuated by moments of rapid transformation. The last era of open oceans was drawing to a close. Ice would soon take its place, and the Earth, for a time, would fall asleep beneath a frozen shell. And so, as the warmth faded and the world began to quiet, the first true whispers of ice emerged. In the stillness to come, a planet would hold its breath, waiting through the long silence for the heat of its own heart to bring it back again. It began so quietly that nothing living could have recognized what was coming. There was no sudden storm, no dramatic plunge into darkness. The first whisper of the ice was almost invisible. The air cooled by degrees that no creature could measure, and the season stretched just a little longer than before. Snow lingered on mountain tops that once melted bare each summer. In valleys, thin sheets of frost glimmered at dawn, retreating more slowly each year. The balance that had held the planet steady for eons was starting to tilt. The engine behind that slow change was a delicate interplay between continents, oceans, sunlight, and the invisible gases that wrapped the planet. Carbon dioxide, the ancient blanket that had kept Earth warm since its youth, was thinning. Weathering of new continental rock had drawn more of it out of the sky. Rainwater mixed with minerals, binding carbon into stone and carrying it to the sea floor. In that slow geological transaction, heat slipped away. The sun, dimmer in that distant era, could no longer make up the difference. Its rays, weaker by a few percent than today's, fell upon a planet increasingly covered in reflective surfaces, bare rocks, bright sand, patches of snow. Every photon that bounced back into space was a little warmth lost. Over time, those small losses added up to a global drift toward cold. At first, the process might have seemed benign. The polar caps grew thicker, but they had come and gone before. Ice advancing into high latitudes was nothing new. The cycle of warming and cooling had shaped Earth for billions of years. Yet this time, something was different. The continents were in the wrong places. Much of Earth's land sat near the equator, where sunlight is most intense. Normally the tropics act as the planet's heat engine, absorbing energy and redistributing it toward the poles. But when land replaces ocean in those regions, that heat engine weakens. Land reflects more sunlight than water, and when that land begins to gather snow, the reflection grows stronger still. Geologists call this the albedo effect. The brighter the surface, the more sunlight it bounces away. It is a simple mechanism with profound consequences. A little extra brightness at the equator means less heat absorbed overall. Less heat means more snow, more reflection, more cooling. The feedback is self-reinforcing, elegant in its simplicity and merciless in its results. Scientists studying ancient rocks have found evidence of this transformation written in their chemistry. Layers of glacial tillite, sediment left behind by glaciers, appear in tropical regions that, according to magnetic data, once lay near 0 latitude. Mixed among them are marine deposits, showing that glaciers reached all the way to sea level. These are not the scars of a local cold snap. They are signatures of a world beginning to freeze from the equator outward. The ocean played a central role in amplifying the change. As temperatures dropped, cold water sank, disrupting the currents that carried warmth from equatorial to polar regions. With circulation weakened, heat became trapped near the surface in some places and lost more rapidly in others. The deep ocean grew isolated, its chemistry shifting as oxygen levels fell. That change affected the delicate balance of gases exchanged between sea and air, drawing down even more carbon dioxide. The Earth was, in effect, breathing more deeply, but exhaling warmth instead of retaining it. On the surface, storms may have grown less frequent but more violent when they occurred. Cooler air holds less moisture, yet temperature contrasts between regions can drive intense winds. The planet's climate system was moving toward instability, and in that unstable dance, weather became erratic. Some years might have brought torrential rains to the coasts, carving new deltas and spreading sediments rich in nutrients. Others might have been parched, leaving salt flats and dry basins where water once pooled. The extremes would have accelerated erosion, feeding the same chemical reactions that removed carbon from the air. It was a slow spiral, each loop colder than the last. For life in the oceans, the first signs of change may have been felt as a subtle shift in currents and light. Algae and cyanobacteria that relied on sunlight found themselves in dimmer waters as dust and minerals from increased erosion clouded the seas. Cooler temperatures slowed their metabolism. Some species may have perished quietly, unable to adapt to the reduced light. Others developed resilience, forming spores or cysts that could endure long periods of cold and darkness. In the shallows, microbial mats clung to rocks, continuing their slow photosynthesis under weakening rays. They had survived worse before: asteroid impacts, ultraviolet radiation and chemical chaos. A little ice was just another test. At the same time, volcanic activity continued to pulse across the planet. Beneath the crust, the Earth's interior was as restless as ever, its heat unbothered by surface chills. Lava erupted from fissures and mountains, spreading across the land in slow, glowing waves. These eruptions released carbon dioxide and sulfur dioxide into the atmosphere. Ordinarily, such gases would warm the planet, but the cooling had already outpaced the volcanic contribution. The sulfur formed reflective aerosols high in the sky, which temporarily shaded the surface even more. What should have been a stabilizing influence instead deepened the descent into cold. Each winter grew longer, each summer shorter. Glaciers that once retreated now lingered year-round. Snow fell farther from the poles. In the tropics, occasional frosts began to appear, thin crystals forming on rocks before sunrise. It is possible that clouds thickened as the atmosphere cooled, scattering sunlight and reducing the warmth that reached the ground. Slowly, imperceptibly, the Earth's climate crossed a line it would not return from for millions of years. Scientists trying to reconstruct this time rely on clues left behind in ancient sediments. One key indicator is the presence of so-called cap carbonates, thin layers of carbonate rock that formed abruptly after glacial deposits. These layers suggest that after periods of intense cold, the planet warmed suddenly, releasing massive amounts of carbon dioxide. To produce such swings, there must first have been an extreme drawdown of that gas, followed by its rapid release. It fits the picture of a world oscillating between ice and fire. Before the freeze became global, there may have been regions of striking contrast. Near the equator, sunlight still reached the surface strongly enough to keep some seas open. These were likely fringed by thick ice extending from the continents. Between them lay belts of cold water and floating icebergs. The atmosphere would have carried fine dust blown from the growing ice sheets. It might have looked like a pale haze muting the sunlight that struggled through. If you could have watched the Earth from orbit during this time, you would have seen the polar caps expanding like slow tides, inching toward the middle latitudes. The dark blues of the oceans faded as more and more of the planet turned white. Even the deserts might have glittered with frost in the early light. It would not yet have been the fully frozen marble of later ages, but the transformation was underway. The cause of this runaway effect still stirs debate among scientists. Some propose that the breakup of Rodinia exposed vast new areas of silicate rock, accelerating chemical weathering and carbon removal. Others point to a possible reduction in volcanic activity, which would have limited the replenishment of atmospheric carbon dioxide. Still others suggest biological factors, the evolution of new photosynthetic organisms that captured carbon more efficiently. The truth is likely a combination of all these forces, layered over millions of years. Planetary change is rarely the result of a single trigger. It is the outcome of countless small events woven together. Another subtle influence may have come from the tilt of Earth's axis and its orbit around the Sun. Even small variations in these parameters, the so-called Milankovitch cycles, affect how sunlight is distributed across the surface. During certain alignments, summers become cooler at high latitudes, allowing ice to accumulate rather than melt. If such a cycle coincided with already declining greenhouse gases, the result could have been the perfect storm for glaciation. Once the process began, no mechanism strong enough remained to reverse it quickly. The formation of ice itself transformed the planet's appearance. Ice sheets grow not merely upward but outward, creeping slowly across land, grinding rock beneath them into fine powder. That powder, known as glacial flour, washed into the oceans when meltwater flowed beneath the ice. In the modern world, such sediment gives glacial streams a milky turquoise colour. In the pre-snowball world, it may have tinted coastal seas, turning them cloudy and dull. This influx of minerals altered ocean chemistry, changing the balance of nutrients and potentially triggering blooms of microorganisms that briefly flourished before conditions became too harsh. The first glaciers of the Cryogenian would have been immense beyond modern comparison. Some extended thousands of kilometres from their centres, reaching sea level and carving into the ocean. Where ice met water, towering cliffs broke apart into icebergs that drifted into warmer currents, releasing stones and debris as they melted. These drop stones settled gently through the water column, embedding themselves in soft marine mud. Millions of years later, they would be found in tropical regions, silent witnesses to the impossible, a frozen equator. As more sunlight reflected away, the ocean surface cooled further, increasing the formation of sea ice. The boundary between frozen and open water moved steadily toward the equator. In places, the ice may have grown several kilometres thick. Underneath, the ocean remained liquid, kept from solidifying entirely by heat rising from the mantle and the pressure of the overlying ice. Within that dim, cold water, life endured. Microbes near volcanic vents continued to metabolize chemicals seeping from the crust. Others drifted near the base of the ice, feeding on nutrients released from trapped sediments. In these hidden refuges, evolution did not stop. It simply slowed. The atmosphere above this frozen world changed character as well. With less evaporation from the oceans, humidity declined. Rainfall diminished, replaced by rare snow that fell lightly and remained unmelted. Dust storms may have swept across exposed continental shelves, spreading fine particles that settled on the ice like faint shadows. Over time, this dust could have influenced the planet's albedo, darkening small areas and absorbing a bit more sunlight. But by then, the balance had shifted too far. The ice had momentum, and the cooling continued. Even in this desolation, geological processes carried on beneath the surface. Tectonic plates moved, continents drifted, and volcanoes erupted. Each eruption was a small pulse of resistance, releasing gases that sought to warm the sky. Over millions of years, these emissions would accumulate, setting the stage for the planet's eventual recovery. But for now, they were whispers against the vast silence of ice. The Cryogenian glaciations were not identical events. The earlier Sturgeon glaciation may have been the more severe, lasting perhaps 50 million years. It was followed, after a brief interlude, by the Marinoan glaciation, shorter but nearly as intense. The first whisper of ice marked the beginning of the Sturtian. From that point on, the world's descent was irreversible, until the very chemistry of the atmosphere changed again. Modern researchers try to imagine what it would have looked like to stand on that frozen world. The horizon might have been stark, the air thin, the light diffuse as if seen through frosted glass. Sound would have carried differently, muffled by snow and ice. There would be no scent of vegetation, only the faint tang of minerals and cold salt. The ocean, sealed beneath its lid, would move silently, currents reshaping in the darkness below. It was an alien Earth, and yet it was still home, the same planet that would one day cradle forests, animals and people. Each clue we uncover from that time, each mineral grain or isotope ratio, tells us not just about the physics of climate, but about the fragility of balance. A few molecules in the air, a shift in a continent's position, a change in sunlight. These were enough to turn an entire world into ice. Yet even as the freeze deepened, forces were already gathering that would one day thaw it. Carbon dioxide from volcanoes, heat from the core, and the stubborn persistence of life would all play their parts in restoring warmth. For now, though, the first whisper of ice had become a murmur spreading across oceans and continents alike. The frost that began on mountain peaks had crept down to the shores, and the mirror of the planet grew brighter each year. The next stage would come soon, the time when the world, once vibrant and liquid, would transform fully into a sphere of white, sealed in silence and light. The transformation from frost to a frozen world did not arrive with thunder. It crept in softly, as if the planet simply exhaled and never drew its next warm breath. The last traces of open sea slowly sealed beneath sheets of ice that thickened year after year, until nothing remained uncovered. What began as scattered glaciers and snowfields joined together in a seamless expanse, stretching unbroken from pole to pole. It was not merely an ice age, it was an ice world. From the orbit of the moon, Earth would have appeared not blue and green, but pale, bright, and almost metallic, its oceans hidden under kilometres of frozen water that reflected sunlight like mirrors. The phrase, "white horizons without end," is not an exaggeration. There were no forests to interrupt the light, no rivers carving through soil, no green patches to absorb warmth. Everything that once shimmered and moved had turned solid and still. The equator, once the line of heat and energy, was indistinguishable from the poles. It glittered under the same hard glare of the sun. The continents, welded together by ice, became indistinct beneath the weight. Only the tallest peaks occasionally pierced through the white crust like the spines of a submerged world. Beneath them, glaciers ground the rock to powder, carrying traces of entire mountains toward the sea. The ice itself was not a smooth plain, but a landscape of subtle shapes. Ridges, fractures, and ridgelines formed as frozen sheets pushed and folded against one another. Crevasses opened where the surface stretched. In other areas, pressure welded ice together into thick crystalline masses that shifted almost imperceptibly. Over thousands of years, those slow movements would shape the geology beneath, leaving behind grooves and striations we can still find today. The planet had become a sculptor, carving itself with patience measured in eons. Beneath the surface, the oceans remained liquid, trapped beneath an icy shell that may have been 1 to several kilometres thick. Darkness ruled there. The sunlight that filtered through the upper ice reached only the first few metres before scattering into faint bluish shadows. The temperature of that hidden ocean hovered near freezing, but it did not freeze entirely. Heat from the planet's core continued to rise through the seafloor, leaking from hydrothermal vents and spreading faint warmth through the deep. Those vents became sanctuaries for life, providing energy and chemical nutrients to organisms that could tolerate the cold. The creatures of that world were microscopic, yet they held on. Bacteria and archaea clustered around vents, feeding on hydrogen sulfide and iron compounds. Some formed mats on the seafloor, while others drifted in the dark water above, dividing slowly, preserving themselves in near stasis. Above them, beneath the ice, pockets of salty water and brine channels offered other refuges. Within those narrow veins, small microbial colonies might have endured, shielded from total darkness by the faint glow filtering through thin ice near volcanic regions. The chemistry of the ocean changed dramatically under this seal. With no open surface for exchange, oxygen levels declined. Carbon dioxide, released by volcanoes and hydrothermal vents, dissolved into the water, forming weak acids that reacted with minerals on the seafloor. The cycle of gases between air and sea that once regulated climate had stopped. The Earth's atmosphere, thin and cold, grew heavy with carbon dioxide, accumulating gradually as volcanoes continued to erupt. The ice prevented the gas from being reabsorbed by the ocean, and so the atmosphere thickened over millions of years, storing the warmth that would one day bring the thaw. But during this frozen chapter, the accumulation was imperceptible. The surface conditions were extreme. Average global temperatures may have fallen to minus 50 degrees Celsius, colder than the most frigid Antarctic nights today. Winds swept across the plains of ice with little resistance, carving snow into sharp ridges called sastrugi. Dust, blown from exposed volcanic regions, settled across the surface in thin layers, faintly darkening the snow in some areas and changing how it reflected light. But even with these blemishes, the overall brightness of the planet kept it locked in its deep freeze. Sunlight bounced away into space, leaving the surface almost untouched by warmth. What few volcanoes broke through the ice would have created surreal landscapes, black rock surrounded by blinding white. Around their vents, steam rose and froze in the air, forming crystalline plumes that drifted downwind. Lava, meeting the ice, generated explosions of steam that carved pits and caves. These oases of heat may have provided rare habitats where liquid water existed in open form. It is possible that life clustered around such places, forming ecosystems based on chemical energy rather than sunlight. Above, the sky would have been pale and still. With less moisture to form clouds, the atmosphere was mostly clear, a faint blue during the day and black at night. The stars shone with unbroken clarity, their light reflecting from the planet's frozen face. Auroras may have danced more vividly across the high latitudes as the solar wind interacted with Earth's magnetic field. Their shifting curtains of green and violet would have been one of the few moving lights in a world otherwise motionless. The ice did not remain entirely static. Over time, its immense weight pressed down on the crust, causing land masses to sink slightly. Where the ice sheets were thickest, the crust depressed by hundreds of meters. This deformation changed the shape of the seafloor and the flow of subterranean heat. When the ice eventually melted millions of years later, the land would rebound slowly, leaving scars that geologists still trace in ancient rocks. These glacial imprints, scratches, grooves and dropstones, are some of the strongest evidence that the world once lay frozen from edge to edge. Despite the vastness of the ice, the planet was not entirely uniform. Regions near active volcanoes or areas where the crust was thin might have remained slightly warmer. There the ice could have been thinner or punctuated by cracks. Such cracks may have opened temporary windows to the ocean below, allowing gases to escape. When pressure built up beneath the ice, fissures could have vented steam or carbon dioxide in violent bursts. These events would have been short-lived but significant, adding to the slow accumulation of greenhouse gases in the atmosphere. The Earth's internal heat was not idle during this time. Beneath the frozen surface, tectonic activity continued. Continents drifted slowly, perhaps at different rates due to the altered distribution of weight. Seafloor spreading at mid-ocean ridges persisted, creating new crust and releasing heat and gas into the ocean above. Although sealed under ice, these ridges were critical in maintaining the planet's livable core. They supplied chemical gradients that fed deep-sea life and acted as exhaust valves for Earth's trapped energy. Meanwhile, on the surface, The quiet stretched on for millions of years. The cycle of day and night continued, but it no longer shaped weather or growth. The sun rose and set over a frozen mirror, its light scattering without effect. Each sunrise looked much like the last, casting long shadows across the ridged ice. The moon's pull still created tides, but the ice flexed only slightly in response. The ocean beneath moved slowly, its currents weakened but persistent, guided by the rotation of the planet and the uneven distribution of heat from below. For any observer, if one could have existed, the silence would have been immense. The absence of running water, rustling leaves, or animal movement meant that sound itself was rare. Only the occasional cracking of ice or the distant rumble of a buried volcano might have broken the stillness. The air would have been so dry that even a shout might not carry far. It was a planet asleep, conserving its energy in a long, dreamless pause. Yet beneath this apparent stillness, change continued in hidden forms. Chemical reactions between rocks, water, and air were still taking place, albeit slowly. Volcanic gases continued to build in the atmosphere, increasing the concentration of carbon dioxide. Over millions of years, this accumulation would reach a critical threshold. But during the frozen interval, the effect was negligible compared to the relentless reflection of sunlight. The planet was locked in a feedback loop where cold reinforced cold, and brightness guarded the ice like a fortress. The formation of ice sheets across the continents had other consequences. As the oceans froze and contracted, sea levels dropped dramatically, perhaps by hundreds of meters. Shallow seas disappeared, exposing continental shelves that had been underwater for eons. These newly exposed surfaces were quickly covered by snow and ice, further increasing the planet's reflectivity. The weight of this ice altered Earth's gravitational balance, subtly affecting how the planet rotated. Some scientists suggest that the redistribution of mass could have shifted the poles slightly, though such movements are difficult to measure after so much time. The minerals trapped within the ice tell part of the story. Dust from volcanic eruptions settled into layers, marking time like rings in a tree. Each eruption added a thin stripe of ash, later buried by more snow and compacted into ice. When the ice eventually melted, these layers dissolved into the sea, releasing a sudden pulse of nutrients that would later fuel a burst of biological activity. The frozen world was storing potential energy in chemical form, waiting to be released. Even as the world froze over, faint traces of colour still existed. In places where microorganisms clung to the underside of the ice, pigments within their cells gave off reddish or brownish hues. These streaks might have tinted parts of the frozen surface, faint reminders of life's persistence. Similar phenomena can be seen today in the blood-red snow of polar regions, caused by algae that bloom in cold, wet environments. If such colours appeared during the Cryogenian, they would have been rare and fleeting, quickly buried beneath new snowfall. Scientists have often wondered how long the planet remained in this frozen state. Estimates vary, but some suggest tens of millions of years for each glaciation event. That timescale is almost incomprehensible to human minds. Entire mountain ranges could rise and erode while the ice persisted. Over such durations, even small processes accumulate vast effects. The volcanic gases released steadily from Earth's interior, trapped under the icy lid, eventually thickened the atmosphere enough to begin reversing the trend. But during the long middle period, nothing seemed to change. From a distance, the planet might have appeared peaceful, but it was under immense stress. The temperature difference between the surface and the deep interior created mechanical strain. Heat trapped below the ice could have generated subglacial melting in some regions, forming vast lakes beneath the sheets. When pressure built up, those lakes may have drained suddenly, sending torrents of water beneath the ice and reshaping the land. The sudden release of such water could have caused fractures and temporary collapses in the ice cover, producing plumes of steam and new flows of sediment. The evidence for these hidden movements can still be found in ancient deposits. Certain rock formations show signs of sudden flooding followed by renewed freezing. Others record chemical changes consistent with brief intervals of oxygenation when trapped water reconnected with the air. These were momentary interruptions in the planet's deep hibernation, flickers of motion in an otherwise static world. The balance between cold and heat was fragile but self-sustaining. For the ice to persist, the planet's average temperature only needed to remain a few degrees below freezing. As long as the albedo feedback kept reflecting sunlight away, the frozen state would continue. The faint warmth from the core could not penetrate far enough to thaw the surface, and the weak sun of that era offered little assistance. Earth had become its own mirror, trapping itself in brightness. For modern scientists, reconstructing this world requires patience and imagination. They analyse isotopes of oxygen and carbon in ancient rocks to infer temperature changes. They examine glacial deposits found in equatorial regions to confirm how far the ice spread. They model the interactions of gases, sunlight and surface reflectivity to understand how such an event could happen, and, just as importantly, how it could end. Each piece of evidence adds detail to the picture, revealing a planet that nearly froze solid yet somehow avoided total extinction. The frozen Earth also raises questions about life elsewhere in the universe. If a planet can endure such extremes and recover, then perhaps similar resilience could exist beyond our world. The idea of oceans hidden beneath an ice, sustained by geothermal heat, echoes in our studies of moons like Europa and Enceladus. The story of Earth's deep freeze is not just history, it is a guidebook for understanding how life might persist in the coldest places imaginable. As the white horizons stretched endlessly across continents and oceans alike, the Earth waited. It could not remain frozen forever. Each volcanic eruption sent more carbon dioxide into the air. The greenhouse gases trapped beneath the ice continued to build. Slowly, the balance began to shift once again. The brightness that had protected the cold would one day yield to warmth, but that moment was still far in the future. For now, the planet rested in its frozen stillness, its beauty austere and silent, its future hidden beneath the snow. Deep below, the volcanic breath of the world continued, invisible yet relentless. Carbon dioxide seeped upward through cracks, gathering in the sky above the ice. As millions of years passed, the accumulation grew, and the planet's own exhaust would become its salvation. The next transformation, when it came, would not be gentle. The thaw would arrive with floods, storms and chemical upheaval. But before that rebirth, Earth lingered in its frozen reflection, a pale world turning slowly in the dark, a silent testament to both the fragility and endurance of a living planet that never truly stopped breathing beneath the ice. The light that reached Earth during its long freeze was unlike anything that had touched it before. It came weakly through a thinner atmosphere, scattered by the crystals of ice that filled the sky, reflected again and again until it became more glow than warmth. To anyone who could have stood upon that frozen crust, the horizon would have appeared brighter than the sun itself, a band of brilliance that stretched unbroken in all directions. The world had become a sky of mirrors, every surface casting light back into space, leaving the planet bathed not in heat, but in an endless shimmer of cold illumination. The transformation of a light was as important as the ice itself. Before the freeze, the oceans had absorbed sunlight, converting it into warmth and movement. Dark water is efficient at drinking light, keeping a planet alive with its stored heat. But now that same light struck a surface as hard and bright as polished stone. The ice returned it upward, sending it back through the thin veil of air and into the emptiness beyond. What little radiation the Earth kept was trapped beneath the ice, unable to penetrate the mirrored shell that covered the world. In a sense, the planet had turned against its own star, rejecting the energy that once sustained it. The science behind that reflection is simple, though the outcome was profound. The ratio of reflected to absorbed light is called albedo, a measure of how bright a surface is. Snow and ice have an extraordinarily high albedo. When large areas become covered in them, the effect compounds. More light reflected means less heat absorbed. Less heat means colder air, which allows more ice to form, which in turn increases reflection again. It is a self-reinforcing loop, and during the Cryogenian, it drove the planet into its deepest freeze. Above the frozen land and sea, the atmosphere itself acted as a second mirror. The lower layers contained fine ice crystals suspended in the cold air, forming halos and arcs around the sun. Cirrus-like veils stretched across the heavens, diffusing light into soft gradients of white and blue. Sunlight entered these layers and split, creating faint rings and pillars of brightness. The familiar blue of modern skies would have been paler, perhaps even silvery. The air was dry, stripped of most moisture, and so clouds were rare, but when they formed, they glittered faintly like powdered glass. At night, the reflection did not end. The moonlight, already pale, found itself multiplied by the same icy surfaces. Shadows were sharp yet faint, stretching over terrain that glowed faintly with its own reflected sheen. Starlight, normally too weak to illuminate, might have been visible bouncing off the horizon, a diffuse glow from the distant constellations scattered across the ice. The planet was brighter at night than it had ever been in its history, but it was a cold brightness, a sterile radiance that gave nothing back. Within this mirrored world, heat flowed in strange and limited ways. With the upper layers sealed in ice, most warmth came from below. Volcanic heat rising from the mantle warmed the ocean's bottom waters, setting up slow convection currents that moved under the ice. These currents carried nutrients and gases, feeding microbial life that clung to existence in the dark. But the surface above remained almost entirely decoupled from these processes. The cold trapped above and the warmth trapped below rarely met. The planet had split into two worlds, one frozen and reflective, the other hidden and simmering in silence. Geologists believe that the albedo of the Snowball Earth could have been as high as 70 or even 80%. That means the planet was reflecting up to 4/5 of the sunlight it received. For comparison, today's Earth reflects about 30%. This difference, small in number but vast in effect, explains why the planet's temperature plummeted so drastically. It also explains why the freeze was so difficult to reverse. Once the ice reached the equator, there was little chance for the system to recover on its own. The mirrors of the Earth were too efficient, too relentless. This mirror world also reshaped the chemistry of the atmosphere. With most of the ocean sealed off, the exchange of gases between air and sea stopped. Carbon dioxide released by volcanoes no longer dissolved readily into the water, so it began to build up slowly in the air. Methane, another potent greenhouse gas, was broken down by sunlight in the thin upper atmosphere, leaving mostly carbon dioxide behind. The result was a strange paradox. The planet was freezing while its greenhouse gases were quietly accumulating. It was only a matter of time, measured not in centuries but in millions of years, before that build-up tipped the balance again. The physical appearance of the ice would have varied from place to place. In some regions it was likely clear and compacted, like glacial ice on modern Antarctica. In others, wind-blown snow created layers of frost that sparkled under the faint sun. Where dust settled from volcanic eruptions, the surface turned slightly darker, absorbing marginally more heat. Those regions might have melted briefly during rare warm spells, forming pools of meltwater that quickly refroze. Such transient features would have been scattered across the planet, small blemishes on an otherwise uniform world. From orbit, the Earth might have looked alive with light, but the brightness hid an absence. The oceans, once a dynamic blue, were still and white. The continents, covered by ice kilometers thick, no longer showed their outlines. Even the air currents that shaped weather systems had slowed to a crawl. The usual cycle of evaporation, condensation, and rainfall that defines a planet's living atmosphere had nearly stopped. The hydrological system had gone dormant. In its place was a slow sublimation cycle, ice turning directly into vapour under sunlight, and then freezing again when temperatures dropped. Scientists studying this period have noted that the absence of liquid water at the surface would have drastically reduced erosion. Mountains would have been preserved longer, and sediment transport would have slowed. However, glacial activity continued beneath the ice. As the glaciers moved, they scraped away rock, grinding it into fine particles. These sediments collected at the base of the ice sheets and were occasionally carried to the ocean through subglacial channels. When the ice later melted, these sediments were deposited across vast areas, forming characteristic layers of glacial till that are found in rocks today. Despite the extreme cold, the planet's interior continued to function normally. Tectonic plates moved slowly, carrying continents across the buried ocean floor. As they shifted, new volcanoes emerged, pushing through cracks in the ice. Each eruption was both a local disruption and a global contribution. Locally, the heat melted surrounding ice, forming temporary lakes and rivers that released steam into the air. Globally, the gases released, especially carbon dioxide, added to the gradual build-up in the atmosphere. Over millions of years, this accumulation would reach levels hundreds of times higher than today's, enough to eventually overcome the planet's reflectivity. But that thaw was still far away. For the moment, the frozen Earth remained a stable system, stable in its lifelessness, stable in its repetition. The days and nights passed with little difference. The axial tilt of the planet continued to produce seasons, but those seasons were muted. The polar regions, always cold, grew marginally colder during winter. The equator, which once received direct sunlight, remained near freezing even at its warmest. The contrast between regions diminished. The planet's climate, normally full of gradients and flows, flattened into uniformity. In the midst of this uniform cold, life persisted in unexpected ways. Microbes adapted to the darkness found niches within the ice itself. In thin layers where impurities collected, salts, minerals, or trapped gas bubbles, small pockets of liquid water could remain even below freezing. These briny microenvironments provided habitats for extremophils, organisms capable of surviving extreme conditions. Modern analogues exist in the polar ice sheets of Antarctica, where microbial colonies live within the ice, metabolizing slowly but continuously. It is likely that similar communities existed during the Cryogenian, clinging to existence in the frozen matrix. Chemical energy from the deep sea vents sustained another form of survival. Microbes there used chemosynthesis to convert dissolved chemicals into energy, independent of sunlight. These ecosystems, though limited in diversity, may have been the ancestors of many modern extremophiles. Their persistence through the Snowball Earth episodes suggests that life never came close to extinction, even when the surface conditions were uninhabitable. The continuity of microbial evolution through these times is one of the reasons Earth could rebound so dramatically afterward. While the mirror-like brightness maintained the cold, it also created unique atmospheric phenomena. The thin air and reflective surface would have amplified optical effects. Sundogs, bright spots appearing on either side of the sun, would have been common, caused by sunlight refracting through hexagonal ice crystals suspended in the atmosphere. Halos, arcs, and columns of light might have been visible daily, creating an eerie beauty across the pale sky. These displays, similar to those occasionally seen in polar regions today, would have been global, constant reminders of the frozen air above and below. Another phenomenon likely present was the suppression of convection. In modern times, warm air rising from the surface drives circulation and weather. In the Snowball Earth, the cold surface meant little warm air to lift. As a result, the troposphere, the lowest layer of the atmosphere, became shallow and stable. Winds weakened and precipitation became rare. When snow did fall, it might have been composed of fine ice crystals drifting gently downward for hours, accumulating slowly but steadily. There were no blizzards, only quiet and persistence. Over time, as volcanic gases accumulated and sunlight continued to fall on the ice, the balance began to shift slightly. The greenhouse effect strengthened, but the albedo feedback still dominated. The transition between these forces was slow, oscillating over millions of years. Some models suggest that brief periods of partial melting may have occurred near the equator, only to be followed by renewed freezing. These cycles could have left chemical signatures in the sediments, marking the slow tug-of-war between heat and cold. One of the striking aspects of this era is how long it lasted relative to the history of life. The Cryogenian glaciations together spanned tens of millions of years, longer than the time separating the extinction of the dinosaurs from today. During that interval, evolution continued in the oceans beneath the ice. When conditions finally improved, the organisms that emerged were more complex than before. Some scientists think the stress of survival in extreme environments drove the evolution of multicellularity, as cooperation offered an advantage. If that is true, then the frozen mirror world was not just a period of stasis, but a crucible for the development of life as we know it. The sky of mirrors in this sense was both a barrier and a womb. It isolated the planet, cutting off sunlight and warmth, yet it preserved the deep oceans from complete freezing. It allowed chemical cycles to continue below while protecting them from further cooling above. The very reflectivity that seemed to end life's progress may have created the conditions for its renewal. By sealing the oceans, it kept volatile gases and nutrients trapped until the eventual thaw. When the ice finally retreated, those nutrients would pour into the sunlight, fueling an explosion of biological diversity. For the moment, however, the planet remained motionless, still caught in the brilliance of its own reflection. The continents slept beneath their icy armour, the oceans murmured below, and the atmosphere glowed faintly in the sunlight. It was a world of frozen equilibrium, balanced between extinction and endurance. The mirrors that encased it gave nothing away, reflecting light so perfectly that even time itself seemed to slow. In that extended silence, the mechanisms of recovery were already beginning to stir. Each volcanic eruption added its faint breath of warmth. Each molecule of carbon dioxide that escaped into the air became part of the long path toward restoration. The build-up was invisible, incremental, and inevitable. One day, the sky of mirrors would begin to dim, the ice would no longer reflect so much light, the balance would tilt, and the world would awaken. But for now, the planet remained wrapped in its cold luminescence, patient and unhurried, a reflective sphere turning through space, waiting for its next transformation to begin. Beneath the hard shell of the frozen oceans, where sunlight filtered through kilometers of compacted ice, life did not end. It waited. The ice above acted like glass, translucent in some places, opaque in others, and though it sealed the planet in silence, it also protected what little warmth remained below. The surface world had become an endless mirror of snow and frost, but underneath, an invisible persistence continued. Life had already survived billions of years of change, and it was not ready to disappear. The ocean under the ice was a strange, layered world. Near the bottom, hydrothermal vents erupted from cracks in the crust, releasing heat and minerals into the water. Around them, the darkness pulsed with faint energy. These vents had been present long before the ice came, and they did not stop when the surface froze. Instead, they became lifelines, oases of warmth and chemistry in a global sea of cold. Microbes clustered around them, feeding on the gases that spewed from the Earth's interior: hydrogen sulfide, methane, and carbon dioxide. In the absence of sunlight, they used chemistry to survive, converting those compounds into energy through reactions that had powered life since its very beginnings. This kind of metabolism, chemosynthesis, is still found today in the deep oceans. It doesn't depend on light or photosynthesis, only on the right gradients of heat and chemical imbalance. In the Cryogenian ocean, these gradients were abundant. The vents released superheated fluids rich in metals and sulfur, while the surrounding water remained near freezing. Where the two met, life found opportunity. Microbial mats grew in clusters, forming dense layers that trapped minerals and built small chimneys of rock. The structures grew slowly but steadily, recording the steady output of the planet's hidden furnace. Further from the vents, in colder, darker regions, life adapted differently. Some organisms drifted near the interface where the base of the ice met the water. There the ice was not perfectly solid. It contained channels and brine pockets, narrow veins where salts and gases concentrated. These tiny spaces could remain liquid even at temperatures far below the freezing point of pure water, because the salt lowered the temperature at which ice formed. Within those pockets, microscopic communities could persist, cycling nutrients and exchanging gases with the ocean below. Modern studies of Antarctic sea ice reveal similar ecosystems. Under thick sheets of ice, bacteria, algae, and small protozoa live in thin films of liquid water. They survive in darkness for months, relying on stored energy and trace nutrients. When light returns in the brief polar summer, they bloom rapidly, producing pigments that stain the ice red or brown. The Cryogenian world may have looked much the same beneath its frozen lid. Though sunlight was weak, a faint glow might have reached shallow areas near volcanic islands or thinner parts of the ice. There, photosynthetic microbes could have gathered just enough light to sustain themselves. In these hidden habitats, the rules of survival changed. Growth was slow. Metabolism operated at a fraction of normal speed. Some cells likely entered dormant states, forming resistant cysts or spores that could withstand years of extreme cold. Others relied on symbiotic relationships, sharing resources within thin biofilms. The rhythm of life shifted from daily cycles to geological patience. Entire generations may have passed before significant change occurred. Yet even in that slow motion, evolution continued. Mutations accumulated. New strategies emerged for tolerating salt, pressure, and darkness. The chemistry of the trapped ocean was different from what it had been before the freeze. With the surface sealed off, oxygen levels declined. Carbon dioxide dissolved from volcanic emissions at the sea floor, forming weak carbonic acid that reacted with minerals and released ions like calcium, iron, and magnesium. These ions enriched the water, altering its composition. Hydrogen sulfide, produced by microbes or released from vents, built up in some regions, creating layers of toxic water where only specialized bacteria could survive. The ocean was stratified, divided into zones of chemistry rather than temperature. Within this complexity, the boundaries of habitability expanded. Some microbes evolved to use nitrate or sulfate instead of oxygen in their metabolism. Others adapted to high salinity or pressure. The ocean beneath the ice became a patchwork of microhabitats, each with its own chemistry and inhabitants. Some areas were dominated by sulfur-eating organisms, others by methanogens, which produced methane as a byproduct of energy production. That methane may have collected in the upper layers of the ocean, frozen into solid clathrate compounds within the ice. When the thaw eventually came, these compounds would release vast amounts of gas, fueling storms and atmospheric change. It's easy to imagine this world as desolate, but in a way it was still dynamic. The circulation of deep water, though slow, carried nutrients from the vents to other regions. Microbes drifting in the current were transported across vast distances, linking isolated ecosystems. Chemical byproducts from one region became food for another. The global biosphere, though reduced, remained interconnected through the movement of water and the exchange of molecules. Life, even in its smallest forms, kept the planet chemically alive. Geologists searching for evidence of this hidden survival look for specific chemical signatures in ancient rocks. One such marker is the ratio of certain isotopes of sulfur and carbon. During the Cryogenian, these ratios shifted in ways that suggest microbial activity persisted even under extreme conditions. For example, the presence of isotopically light sulfur indicates that bacteria were still metabolizing sulfate, a process that requires life. Similarly, variations in carbon isotopes point to continued photosynthesis, albeit at reduced levels. The rock record, in its quiet language, confirms that life never stopped. The thickness of the ice has been the subject of long debate. Some models suggest it may have been as much as several kilometres thick, while others propose thinner regions, perhaps only a few hundred metres, in areas near volcanic activity or equatorial sunlight. If thinner areas existed, they would have allowed more light to penetrate and more gas exchange with the atmosphere. In those regions, photosynthetic organisms might have flourished during brief interludes of relative warmth. The interplay between these thin and thick regions could have created gradients that supported a surprising variety of life forms. Modern analogues for such environments exist not only in Antarctica, but also on the icy moons of the outer solar system. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both harbour oceans beneath icy crusts. Plumes of water and vapour have been observed erupting from cracks in their surfaces, hinting at hydrothermal activity below. The conditions there, cold, dark and pressurised, are similar to those of Earth during its frozen age. The survival of life during the Cryogenian offers a model for how life might exist elsewhere in the universe, shielded beneath layers of ice yet thriving on chemical energy from below. In the Cryogenian seas, nutrients accumulated over time. With little mixing at the surface, elements like phosphorus and iron settled slowly into the depths. When the ice eventually melted, these nutrients would be released in a massive flush, fueling an unprecedented bloom of life. Some scientists believe this event set the stage for the later rise of multicellular organisms. Before that could happen, however, the biosphere had to endure millions of years of confinement. The ocean was a closed system, recycling its limited resources again and again. One of the most remarkable aspects of life's endurance during this period is its flexibility. Microbes can survive freezing by producing special proteins that prevent ice crystals from forming inside their cells. These antifreeze proteins are still found in many organisms today, from bacteria to fish. Their existence hints that such adaptations may have originated in the Cryogenian, honed by the pressures of surviving under global ice. Other organisms might have used sugars or salts to lower the freezing point of their internal fluids, creating a kind of natural brine that resisted solidification. Evolution, even in near stillness, found ways to preserve itself. The physical structure of the ice may have played a crucial role in this survival. As snow accumulated and compressed, it trapped tiny bubbles of air. These bubbles formed pathways for gas exchange, allowing limited amounts of oxygen and carbon dioxide to move between the ocean and the atmosphere. Though the exchange was slow, it was enough to sustain minimal cycles of respiration and photosynthesis. In this sense, the ice acted not just as a barrier, but as a semi-permeable membrane, a bridge between the living ocean below and the frozen sky above. Occasionally, tectonic or volcanic activity would disrupt this balance. When underwater eruptions occurred, they could melt pockets of ice and release trapped gases into the ocean. These events may have caused brief bursts of warming or changes in ocean chemistry, altering the distribution of life. Afterward, the system would settle again into its slow rhythm. Each pulse of energy, though fleeting, contributed to the gradual accumulation of atmospheric gases that would one day end the freeze. Scientists can trace these intermittent events in ancient sedimentary layers. Thin bands of volcanic ash within glacial deposits mark episodes when eruptions briefly broke through the ice. The minerals within those ashes, rich in iron and trace elements, show signs of rapid oxidation after deposition, an indication that oxygen, however scarce, was still present in the environment. These findings reinforce the idea that the planet's frozen state was not absolute. There were always windows of activity, brief and localized, that kept the biosphere from complete dormancy. The question of how complex life managed to arise after such a severe bottleneck remains one of the great puzzles in Earth's history. The answer likely lies in the resilience and adaptability of these microbial communities. Under the ice, selective pressures were intense. only the most efficient, cooperative and flexible organisms could endure. Those that survived carried the genetic foundations for future complexity. When the thaw finally came and sunlight returned in abundance, those lineages were ready to expand into new forms. Another factor in life's endurance was the slow accumulation of organic matter on the seafloor. Even under ice, dead cells and microbial mats sank over time, creating layers of carbon-rich sediment. These sediments served as reservoirs of potential energy, waiting to be reoxidized when conditions changed. During the thaw, this buried carbon would react with the newly oxygenated water, driving powerful chemical cycles that released energy and reshaped the ocean's chemistry. The stage was being set for an evolutionary leap, though no living thing at the time could have sensed it. In this hidden ocean, the connection between life and geology was absolute. Every volcanic eruption, every slow drift of the continents, every pulse of heat from the planet's core affected the ecosystems below. The balance between heat and cold determined where life could exist. The chemistry of rocks determined what nutrients were available. The very movements of the crust shaped the pathways through which water and gases circulated. There was no separation between biology and geology. They were threads of the same fabric. Over time, the concentration of carbon dioxide in the atmosphere grew higher, trapped above the ice. This gas slowly increased the greenhouse effect, allowing the planet to store more heat from the sun. Eventually that heat would begin to thin the ice and melt the surface. But before that tipping point, the biosphere continued its quiet persistence, unchanged in its determination. The planet was locked in stasis, but life's chemistry never stopped evolving. The image of this hidden world, an ocean beneath glass, is both alien and familiar. The stillness above and the motion below mirror the dual nature of our planet, fragile on the surface, resilient at its core. Even in its darkest, coldest era, Earth remained alive. The ice may have covered everything, but it could not smother the spark that had begun billions of years before. Each microbe beneath the glass was a promise, a quiet assurance that when the cold finally lifted, life would emerge stronger than before, ready to fill the world once again with movement, colour, and sound. And while the world above remained an endless mirror of light, the deep continued to stir. The chemistry of the vents, the slow rise of carbon dioxide, and the hidden warmth accumulating beneath the crust were leading the planet toward its next transformation. The frozen stillness would not last forever. The breath of volcanoes would grow stronger, and the glass ceiling would one day begin to melt. Beneath the weight of ice, the seeds of change were already forming, preparing the silent ocean for the moment when Earth would awaken once more. Far beneath the frozen oceans, where pressure and darkness concealed the restless heart of the planet, heat continued to move. The mantle did not care that the world above was sealed in white. It churned, as it always had, carrying molten rock toward the surface in slow, unstoppable currents. This movement was the pulse of the Earth, and even in the quietest era, it never ceased. The ice above might have trapped the oceans, reflected the sunlight, and muted the sky, but it could not silence the deep. From that depth came the breath of volcanoes, invisible at first, then tangible, then overwhelming. The story of the planet's escape from its frozen state begins with this breath. During the long ages of ice, volcanoes were the only major source of gases entering the atmosphere. Every eruption that pierced the crust, every vent that exhaled along the ocean floor, released carbon dioxide, sulfur dioxide, methane, and steam. On a normal planet, much of that carbon dioxide would have been absorbed by rainwater and sequestered into rocks through weathering. But there was no rain now, and no exposed rock for carbon to bind with. The continents lay buried under kilometres of ice sealed away from the air. That meant the gas had nowhere to go. It gathered in the atmosphere, molecule by molecule, over millions of years. At first, the effect was negligible. The brightness of the planet was absolute. Almost all incoming sunlight bounced away into space. Any heat trapped by greenhouse gases simply radiated back through the thin, reflective atmosphere. But volcanic emissions did not stop. Over immense timescales, they accumulated. Carbon dioxide levels that might once have doubled or tripled during warm periods now rose to hundreds of times their normal concentration. It was a slow process, but time was on the volcano's side. The planet's internal heat was patient. Imagine the scale of it. Beneath every mountain range and frozen valley, magma pushed upward through faults and fractures. On the seafloor, spreading ridges created new crust, releasing gases and minerals into the black water. Some volcanoes erupted beneath the ice, melting pockets of liquid that refroze once the eruptions ceased. Others might have broken through to the surface, their lava fountains briefly painting the white landscape in red and orange before vanishing again under falling snow. Each eruption was brief compared to the age of the ice, but together they formed a continuous exhalation, a planetary sigh that would eventually thaw the world. The build-up of carbon dioxide in the atmosphere changed its structure. As the gas thickened, it began to trap more of the infrared radiation emitted by the planet's surface. At first, the heat was absorbed by the upper atmosphere, creating temperature inversions that slowed the escape of energy into space. The surface remained frozen, but the balance was shifting. The faint warmth that once escaped freely now lingered longer. The greenhouse effect, suppressed for millions of years by the overwhelming brightness of ice, began to reassert itself. Even before the final thaw, volcanoes were reshaping the chemistry of the oceans below. Hydrothermal vents released iron, manganese, and sulfur compounds that built up in the water column. These elements acted as nutrients for the microbial life that still endured beneath the ice. The balance of gases, carbon dioxide, methane, hydrogen sulfide, shifted slowly as biological and geological processes intertwined. The vents provided both energy and instability, keeping the ocean chemically active even as the surface remained still. Geologists studying the Cryogenian rocks have found the traces of this hidden volcanic persistence. In layers of glacial sediment, thin streaks of volcanic ash can still be identified, fine particles of glass and mineral that settled through the water and became trapped in the mud. These ashes carry isotopic signatures of elements like strontium and neodymium that reveal their source in the mantle. By analysing these signals, scientists have reconstructed the timing of volcanic activity and found that eruptions were widespread during the Snowball Earth episodes. The planet's internal fire was not dormant, it was working constantly beneath the ice. Over time, as carbon dioxide accumulated, the greenhouse effect grew stronger than the reflective power of the ice. But before that tipping point arrived, other consequences of volcanic activity played out. Sulfur dioxide, another gas emitted by eruptions, formed aerosols in the upper atmosphere that temporarily cooled the planet even further. These aerosols reflected sunlight directly, enhancing the icy mirror effect. Each major eruption might have produced years of even deeper cold before the aerosols settled or reacted away. The planet's recovery was not smooth. It was a series of small advances and retreats, an uneven struggle between warming and reflection. Eventually, the accumulation of carbon dioxide became overwhelming. Unlike sulfur aerosols, which persist for only a few years, carbon dioxide remains for millennia. Every eruption that added to it compounded the effect of all those before. By the time millions of years had passed, the concentration of greenhouse gases in the air was astronomical. The exact amount is uncertain, but models suggest levels thousands of times higher than those of the modern atmosphere. With such density, even the faint sunlight of the ancient sun could no longer escape freely. When warming began, it did not start uniformly. Near volcanic regions where ice was thinner, melting occurred first. Pools of dark water formed around vents and fissures, absorbing sunlight more effectively than the surrounding ice. These pools grew and connected, forming temporary lakes that steamed faintly in the cold air. The meltwater carried with it dissolved carbon dioxide and minerals from the atmosphere, which in turn reacted with the underlying rock, beginning the slow restoration of the weathering cycle. Each small patch of open water acted as a catalyst for more melting, because dark surfaces absorb heat far better than white ones. As these patches expanded, the planet's albedo began to fall. The reflective surface that had preserved the cold for so long started to darken. This was the crucial moment, a threshold beyond which warming became self-sustaining. Once enough open water existed, the feedback reversed. The newly exposed ocean absorbed sunlight, heating further, melting more ice, and lowering reflectivity still more. The same feedback loop that had frozen the world now began to thaw it. The breath of volcanoes, quiet for so long, had finally reached the surface. This transition was not gentle. As the ice melted, vast amounts of trapped gas were released. Methane clathrates frozen within the ice decomposed, adding another powerful greenhouse gas to the atmosphere. The carbon dioxide already present amplified the warming. Temperatures rose rapidly by geological standards, possibly by tens of degrees in just a few thousand years. The ocean surged as meltwater flooded from the continents, and the planet entered a period of intense volatility. Chemical reactions on the surface accelerated as rock and soil were exposed after millions of years of burial. Rain returned for the first time in ages, acidic from the high carbon dioxide content of the air. It fell on fresh rock, eroding it quickly and washing nutrients into the oceans. The runoff carried vast amounts of calcium and magnesium ions, which combined with carbon dioxide to form carbonate minerals. These reactions drew carbon back out of the atmosphere, eventually stabilizing the climate, but at first the process was chaotic. The evidence of this chaos remains in the rock record as cap carbonates, thick layers of carbonate minerals that lie directly above glacial deposits from the Cryogenian. These layers formed rapidly when the oceans, suddenly rich in dissolved carbon and minerals, precipitated massive amounts of carbonate onto the seafloor. The formation of these caps marks the end of the Snowball Earth phases, the geological signature of the planet's rebirth. Each time the Earth thawed, it left behind one of these markers, silent testimonies to the scale of the transformation. During the height of the thaw, the atmosphere may have resembled that of Venus in miniature, dense, humid, and hot. The surface temperature, once far below freezing, may have soared to tropical levels in a matter of centuries. Intense storms swept across the landscape, driven by the rapid evaporation of meltwater and the enormous difference between air and surface temperatures. Lightning, unseen for millions of years, returned to the sky. Rain fell in sheets, dissolving carbon dioxide and carrying it back into the ocean. The hydrological cycle had awakened. The newly opened oceans teemed with potential. The nutrients that had accumulated under the ice, phosphorus, iron, nitrogen, now mix freely with oxygen from the atmosphere. This combination triggered explosive growth of microorganisms. Algae and cyanobacteria, long constrained by darkness, multiplied rapidly in the sunlight. Their photosynthesis produced oxygen, increasing the gas's concentration in the air and water. The result was a second oxygenation event, a global chemical shift that set the stage for complex life to evolve. The relationship between volcanic activity and biological recovery is intricate. The same eruptions that released greenhouse gases also supplied the trace elements necessary for life. Iron from volcanic ash fertilized the oceans, stimulating productivity. Sulfur compounds provided chemical energy for microbes. The cycle of destruction and renewal was complete. Fire beneath the ice had caused the catastrophe, but also enabled its resolution. On land, the melting ice revealed landscapes that had not seen the sun for tens of millions of years. The ground was raw and barren, scraped clean by glaciers. Rivers carved new valleys through the melting sheets, carrying sediments toward the sea. Over time, these sediments built deltas and continental shelves, laying the foundation for ecosystems that would later develop. The Earth, newly exposed, looked alien. Black rock, steaming water, and skies streaked with vapour. Yet it was alive again, dynamic and breathing. The end of the snowball state did not occur in a single moment. Different regions thawed at different times depending on latitude and local conditions. Some areas may have remained frozen for thousands of years after others had melted. The transition was global, but uneven. Still, by the end of the process, the ice had retreated almost entirely. The oceans were open, the air was warm, and the planet's surface chemistry was once more in motion. In the centuries following the thaw, the planet stabilized into a new equilibrium. Carbon dioxide levels fell as weathering resumed and carbonate rocks formed. Temperatures moderated. The reflective white world gave way to darker season rock, which absorbed sunlight and maintained warmth. The mirror sky that had once trapped the planet in cold now reflected only in patches of cloud and polar ice. The Great Freeze was over, but its legacy endured in the rocks, in the chemistry of the oceans, and in the genetic memory of the life that had survived it. The story of the volcanoes does not end there, though. The heat and gas they released during the Cryogenian reshaped the entire evolution of Earth's atmosphere. By replenishing carbon dioxide and sustaining greenhouse warming, they prevented the planet from becoming permanently frozen. Without them, Earth might have resembled Mars, cold, dry and lifeless. Instead, the slow persistence of volcanic respiration kept the deep carbon cycle alive, ensuring that the planet could recover. Modern measurements of volcanic gases and isotope ratios in ancient rocks confirm how vital this process was. The carbon isotope record shows a dramatic swing at the end of the Snowball Period, corresponding to massive carbon input followed by rapid sequestration. This cycle reflects both the release of gas from volcanoes and its reabsorption during the formation of the cap carbonates. It is a complete loop, a geological breathing pattern that took millions of years to complete. If we could have watched this transformation unfold in real time, it would have seemed impossibly slow yet unrelenting. A world of ice giving way to a world of storms, then to a world of water and rock, then finally to one capable of sustaining lush, oxygen-rich seas. It was a planetary metamorphosis on a scale too vast for human imagination, yet entirely governed by the same physical laws that shape our climate today. The breath of volcanoes, constant and patient, turned the mirror world back into a living planet. It was the slow exhalation that restored movement to the sky, the ocean, and the air. It melted the glass ceiling under which life had waited and brought sunlight back to the surface. With that light came photosynthesis, oxygen, and the foundation for complexity. The Earth had emerged from its long hibernation not diminished but renewed, and as warmth spread through the oceans and new ecosystems began to bloom, the planet was far from stable. The thaw brought turbulence, chemical shifts, and violent storms. Yet within that chaos, life expanded faster than ever before. The frozen silence had given way to motion once more. Beneath the soft breath of the volcanoes, the world began to wake fully, its ice retreating and its air filled again with water vapour and light. The transformation was complete enough to begin another, the slow emergence of diversity, complexity, and eventually the first true gardens of life that would follow in the eras to come. The planet's long sleep ended not with a single moment, but with a gradual stirring that unfolded over thousands of years. The ice that had once seemed eternal began to fracture. Faint seams appeared across its surface, widening into channels through which meltwater flowed in winding paths toward the sea. At first, these streams were no more than thin ribbons, vanishing each night as the air cooled again. But with each passing year, they grew deeper, more persistent, and more confident in their course. The silence that had covered the world for millions of years was breaking, replaced by the low murmur of water finding its way through the thawing crust. From above, the planet's brightness dimmed. where once the entire surface had been a reflective sheet of white, patches of darker colour began to emerge. Melted ice revealed ancient rock, glistening and wet under the weak sun. The contrast between the white expanses and the exposed surfaces altered the balance of light and heat once again. The more the ice melted, the more sunlight the planet absorbed, and the faster the process continued. It was the same feedback loop that had frozen the world, now working in reverse. The equilibrium had shifted. The ice that had locked the planet for eons could no longer hold its grip. The first major floods would have been unimaginable in scale. As the equatorial regions thawed, entire ice sheets collapsed into the ocean. Glacial walls, kilometers thick, fractured and fell, releasing torrents of meltwater that surged outward across the newly exposed land. The oceans rose rapidly, swallowing valleys and basins that had been carved by the ice. Waves and currents scoured the seafloor, mixing layers of sediment that had lain undisturbed for tens of millions of years. In a geological instant, the world changed colour. White faded to blue, and the atmosphere filled once more with the sound of motion. The warming atmosphere carried enormous amounts of moisture, and storms began to circle the planet with violent energy. The air, thick with carbon dioxide and water vapour, became a greenhouse in full effect. Temperatures rose beyond what the surviving life had ever experienced. Rain fell continuously, washing over the continents and reacting with the minerals of newly uncovered rock. These reactions drew carbon dioxide out of the air and locked it into the crust as carbonate minerals, slowly bringing the greenhouse back under control. But for a time, the world was hot, wet, and unstable. It was as if the Earth, after its long stillness, had awoken too quickly and was struggling to find its balance. The chemistry of the oceans transformed as the meltwater poured in. Under the ice, nutrients had built up in isolation. Phosphorus, nitrogen, iron and other elements essential for life. When these reached the open ocean, they acted as a feast for the microorganisms that had survived beneath the ice. Sunlight, once blocked, now penetrated deep into the water, fueling explosive growth. Algae and cyanobacteria multiplied in vast blooms, turning the seas green and filling the air with oxygen. This oxygen began to react with the gases and minerals released by the thaw, oxidizing iron and sulfur compounds that had been stable in the absence of air. The result was one of the most significant chemical shifts in Earth's history. The oxygenation of the atmosphere accelerated dramatically. Rocks that had formed in anoxic conditions began to rust, creating distinctive red layers of iron oxide in the geological record. The ocean, once dark and stratified, became more transparent as the chemistry of the water changed. New ecological zones appeared, surface waters rich in light and nutrients, deeper layers teeming with chemical energy, and the dynamic exchange between them driving evolution forward. The air, though thick and heavy, carried new scents and sounds. Steam rose from warm seas, condensing into clouds that flashed with lightning. Thunder rolled across the landscape, echoing through valleys that had only recently emerged from under ice. The rain carried carbon dioxide from the atmosphere into rivers and lakes, continuing the slow process of stabilization. Over time, this relentless weathering drew enough carbon from the air to cool the planet again, preventing it from overheating. What had been a frozen mirror world was becoming a temperate balance system. This balance, however, took time to achieve. For thousands of years, the planet oscillated between extremes, bursts of heat followed by intervals of cooling, rapid melting followed by slower stabilization. Each pulse left a mark on the surface. The sediments laid down during this period show alternating bands of coarse and fine material, recording cycles of flooding, erosion, and calm. These patterns are the fingerprints of an Earth in transition, shifting from a world dominated by ice to one shaped by water and air once more. For the organisms that had survived the freeze, this was an age of opportunity. The sudden abundance of light and nutrients triggered evolutionary innovation. Some microorganisms developed new pigments to capture sunlight more efficiently. Others adapted to higher levels of oxygen, evolving more complex metabolisms. The foundations of multicellularity, which had emerged tentatively before the Snowball Earth episodes began to take hold. Cooperation between cells, once a rare adaptation, became advantageous in the turbulent new environment. The world's first complex organisms were preparing to appear. Fossil evidence from the period immediately following the Cryogenian supports this view. In rocks dated to around 635 million years ago, scientists have found the earliest signs of multicellular algae and simple animal-like forms. These fossils, though microscopic, show organised structures, evidence of differentiation between cells. This suggests that the harsh conditions of the Snowball Earth may have acted as an evolutionary filter, pushing life to develop new strategies for survival. When the thaw came, those adaptations allowed rapid diversification. The interaction between geology and biology during this time was unprecedented. Volcanic islands, newly exposed above sea level, provided habitats for colonization. The combination of volcanic minerals, heat, and abundant water created ideal conditions for microbial growth. In these regions, chemical weathering proceeded at an accelerated pace, further drawing down carbon dioxide and enriching the oceans with nutrients. The interplay between rock, air, and life formed a feedback system that gradually stabilized the climate. The restoration of the hydrological cycle also reshaped the continents. Rivers carved new channels through the soft, waterlogged sediments left by retreating glaciers. Lakes formed in basins where ice had once pressed the land downward. The rebound of the crust, as the immense weight of the ice was removed, caused slow but steady uplift, creating new mountain ranges and altering drainage patterns. Erosion began anew, carrying sediments toward the sea and building deltas where none had existed before. The landscapes of the modern world were beginning to take shape, sculpted by water rather than ice. The skies, once pale and still, became alive again with movement. Clouds formed in towering columns, driven by the energy of a warming planet. The air carried dust and ash from continuing volcanic eruptions, colouring sunsets in shades of red and gold. Lightning storms lit the horizon, striking newly exposed rock and soil. These flashes of energy may have played a role in the formation of organic molecules, just as they had billions of years earlier when life first began. The atmosphere was not only recovering but evolving, with each storm contributing to the chemistry of the reborn world. The oceans, no longer confined by ice, circulated freely once more. Warm currents carried heat toward the poles, moderating temperatures and preventing a return to deep freeze. Cold water sank near the poles and flowed back along the seafloor, distributing oxygen and nutrients throughout the depths. This global circulation system, re-established after millions of years of stagnation, revitalized marine ecosystems. The mixing of surface and deep waters created stable conditions for photosynthetic life to flourish, setting the stage for more complex food webs. One of the most striking consequences of the thaw was the increase in oxygen, known as the Neoproterozoic oxygenation event. This shift transformed the chemistry of both the atmosphere and the oceans. Higher oxygen levels allowed for more efficient metabolism and the development of larger, more complex organisms. It also led to the oxidation of methane, reducing the concentration of that potent greenhouse gas and further stabilizing the climate. The planet had found a new equilibrium, warmer than before the freeze but not unstable. This period of renewal may have seemed chaotic, but it represented the natural resilience of the Earth system. The same forces that had driven the planet into its frozen state, feedback loops between sunlight, ice and carbon, were now working in reverse to restore balance. The volcanic gases that once seemed destructive became essential to the recovery. The interplay between geological and biological processes demonstrated the planet's capacity for self-regulation. The memory of the ice, however, remained written in stone. Glacial deposits from the Cryogenian are found on every continent, marked by distinctive layers of sediment and dropstones carried by icebergs. Above these layers lie the cap carbonates, smooth and uniform, recording the sudden shift to warmth. Together, these rocks form a global signature, a geological echo of the planet's awakening. They are the archives of a transformation so complete that it redefined the trajectory of life on Earth. In the years following the thaw, the biosphere expanded rapidly. Microbial mats spread across shallow seas, stabilizing sediments and forming the first primitive ecosystems of the new age. Photosynthetic organisms increased oxygen production, enriching the atmosphere further. The surface of the planet, once a uniform expanse of ice, became a mosaic of blue oceans, brown rock and green microbial colonies. The return of colour to the world marked the end of its long monochrome silence. The speed of this recovery challenges the human sense of time. What seems rapid in geological terms still spans tens of thousands of years. To the planet, it was the blink of an eye. To life, it was an era of rebirth. Evolution proceeded at a pace unseen before, as new ecological niches appeared and competition drove innovation. The ocean became the cradle of complexity, a vast, dynamic laboratory where the foundations of animal life were laid. The environmental shifts that accompanied the thaw also influenced the chemistry of the atmosphere. The increased weathering of rocks drew down carbon dioxide more efficiently than volcanic activity could replenish it. Over time, this cooling effect balanced the earlier warming, leading to a stable climate. The greenhouse that had saved the planet from its frozen prison now moderated into a mild warmth, suitable for the flourishing of life. The Earth, once nearly lifeless, had achieved a new kind of equilibrium, one where feedbacks between rock, air and life sustained habitability rather than threatened it. Each stage of this awakening contributed to the next. The return of liquid water led to the revival of the carbon cycle. The renewed carbon cycle stabilized the temperature. The stabilized climate enabled biological diversification. The planet had rebuilt its systems layer by layer, emerging not as a replica of what had been before, but as something entirely new. The Cryogenian had erased much of what existed, but it had also cleared the way for evolution to experiment again from a cleaner slate. The sky, now thick with clouds and vapour, was no longer the pale mirror of the Ice Age. It moved and breathed with the planet's rhythms. The rains that fell were heavy with dissolved carbonates, washing minerals across the continents and into the sea. These minerals, once deposited, would form the limestone and dolomite beds that preserve the memory of this period today. The sound of the rain was a new kind of heartbeat, not the slow creak of ice, but the constant motion of water, an audible sign that the planet was alive again. The long freeze had altered the Earth forever. The continents had drifted, the oceans had changed composition, and life had learned resilience. The world that emerged was not merely a restored version of the past, but a reconfigured system ready for growth. In the eons to come, this renewed planet would give rise to the first animals, the first complex ecosystems, and eventually the vast diversity that defines the modern biosphere. For now, though, the Earth stood at the threshold between its frozen memory and its living future. The air shimmered with warmth, the oceans teemed with green, and the continents steamed under a restless sky. The breath of volcanoes had done its work. The ice was gone, replaced by rivers, storms, and the first hints of stability. The world was awake again, and its next chapter, one of evolution, expansion, and transformation, had already begun to unfold in the shallow sunlit seas where life once again met the light. When the ice had finally gone, the Earth was unrecognisable. The white horizons that had defined it for tens of millions of years were replaced by colour, not just the dull browns and greys of exposed rock, but vivid greens and blues that had not been seen in ages. Oceans shimmered beneath clear skies, rivers braided their way across newly revealed landscapes, carrying minerals from the raw bedrock to the sea. The planet, which had spent so long in silence, was now alive with motion. The air was thick, moist and heavy with the scent of minerals and rain. For the first time in an age, the sun's warmth reached the surface unbroken, and the world answered it with growth. The transformation that followed was unlike anything that had come before. The end of the Cryogenian did not simply mark the melting of ice, it marked the beginning of a new biological order. The Earth's systems, newly reconnected, atmosphere, hydrosphere, biosphere and lithosphere, began to feed one another in ways that had not been possible under ice. The ancient feedback loops that governed climate, carbon and oxygen regained their rhythm. Each element of the planet began to collaborate again, producing balance out of chaos. The ocean, now free of its frozen lid, was where the greatest changes occurred. During the long freeze, nutrients had accumulated in the deep water, trapped and unused. With the thaw, those nutrients rose to the surface, carried by mixing currents. Phosphorus, nitrogen and iron, the essential ingredients for photosynthesis, flooded into the sunlit layers of the ocean. Microorganisms that had endured in darkness suddenly found themselves in a world of light and abundance. They multiplied at a pace that must have transformed the colour of the sea itself. Vast blooms of cyanobacteria and algae spread across entire continents of water, staining them green and turquoise. The oxygen they produced poured into the atmosphere, reshaping it faster than at any time since life began. As oxygen levels rose, the chemistry of the oceans changed profoundly. Elements that had been stable under low oxygen conditions, like iron and sulfur, began to oxidize. This created new minerals, forming sediments of vivid red and orange that still mark this period in the rock record. The ocean floor, once coated in dark anoxic mud, turned to layers of oxygen-rich sediment, a sign that the planet was breathing deeply again. The water became more transparent, allowing sunlight to penetrate deeper, which in turn expanded the range of photosynthetic life. For the first time in hundreds of millions of years, light and oxygen reached into places that had been dark and lifeless. The biological consequences of these changes were extraordinary. In the newly oxygenated seas, organisms could support higher metabolic rates, enabling the evolution of larger and more complex forms. Simple colonies of cells that had survived the Ice Age began to organize themselves in new ways. They shared nutrients, divided tasks, and formed multicellular structures that allowed specialization. This cooperation marked the birth of a new biological architecture, the beginning of complex life. The fossils from this era, known as the Ediacaran period, reveal forms unlike anything alive today. Soft-bodied creatures with quilted surfaces, frond-like appendages and radial symmetry appeared on the ocean floor. They did not yet have skeletons or shells, but they represented a leap in organization. Some grew anchored to the seabed, filtering nutrients from the water. Others may have glided slowly across the sediment, leaving faint traces behind. These organisms were not yet animals as we understand them, but they were the prototypes, the first multicellular beings to explore the possibilities of structure, motion and interaction. The newly stable climate supported this expansion of life. Temperatures had moderated after the intense post-glacial warming, settling into a range that allowed both tropical and temperate conditions to coexist. The continents, freshly exposed, were still barren rock, but chemical weathering continued to release minerals into the sea, fueling productivity. Rivers carried sediments rich in nutrients, and tidal flats provided shallow, sunlit environments where microbial mats could thrive. These mats, made up of dense colonies of cyanobacteria and other microorganisms, trapped sediments and built layered structures that stabilized the seafloor. They were the foundations of ecosystems, providing food and shelter for emerging forms of life. The increased oxygen also transformed the chemistry of the atmosphere itself. Ozone formed in the upper layers, creating a shield against harmful ultraviolet radiation. For the first time, the surface of the planet was protected from the sun's harshest light. This change made it possible for life to expand into shallower and more exposed environments. It was a subtle but revolutionary shift, the creation of a biological safety net that would later allow life to venture onto land. In the oceans, diversity increased dramatically. Microscopic eukaryotes, cells with nuclei and complex internal structures, proliferated. They gave rise to algae, protozoa, and other forms that formed the base of new food webs. Predation, a behaviour largely absent in earlier ages, began to emerge. Some microorganisms evolved to feed on others, driving an evolutionary arms race that encouraged complexity and mobility. This was the beginning of ecological interaction on a new scale, competition, cooperation, and adaptation shaping the course of life. The energy available to organisms grew exponentially. Oxygen allowed cells to extract far more energy from food through respiration than was possible under anaerobic conditions. This surplus of energy made complexity sustainable. It supported larger bodies, longer lifespans, and the development of new biological machinery. Evolution began to accelerate. What had taken hundreds of millions of years before now occurred in tens of millions. The continents themselves were changing as well. The movement of tectonic plates continued, rearranging the world's geography. Mountains rose and eroded. New basins formed and filled with water. Volcanic islands dotted the oceans, their slopes covered in steaming pools and mineral deposits. Each eruption added nutrients and gases to the atmosphere, maintaining the cycles of renewal. Weathering of the newly exposed rock continued to draw down carbon dioxide, keeping the climate stable. The planet had learned to regulate itself again, balancing fire and water, gas and rock, life and air. This renewed stability encouraged the expansion of marine ecosystems. Shallow continental shelves, warmed by sunlight and rich in nutrients, became the cradles of life. Microbial mats gave way to more complex communities, including the first multicellular algae and early animal-like forms. These ecosystems were delicate but self-sustaining. Organic matter from photosynthetic organisms sank into deeper water, feeding decomposers that recycled nutrients back into the system. The biological pump, the process by which life itself influences the chemistry of the planet, was fully active again. The air above the seas began to carry traces of organic compounds released by life. These molecules, though microscopic, influenced the formation of clouds and rain patterns. Even the weather was being subtly shaped by biology. The Earth had become a feedback system not only of geology but of life itself. The garden that followed the ice was not confined to plants and animals, but to the entire network of interactions between living and non-living elements. As the planet continued to recover, the rhythm of day and night resumed its influence on the biosphere. During daylight, photosynthesis drove oxygen production. At night, respiration balanced it. This daily oscillation of gases, measurable even today, began during this period. It was one of the first examples of life setting the tempo for planetary systems. The Earth was no longer just a place where life existed. It was a living, breathing entity whose very cycles were shaped by biology. Fossil evidence from this era shows not only new forms of life, but also new behaviours. Tracks, burrows, and other traces suggest that some organisms had begun to move through sediments in search of food. This was the dawn of motility, the ability to control one's position in the environment. The ocean floor, once covered in passive mats of microbes, now showed signs of activity. Sediments were turned over, oxygen penetrated deeper, and ecosystems became more dynamic. Each movement reshaped the chemical and physical structure of the habitat, creating more opportunities for diversity. As multicellular life became established, ecological relationships grew more complex. Symbiosis, predation, and competition all emerged as driving forces. Some organisms formed partnerships, algae living within other cells, sharing photosynthetic energy in exchange for protection. Others evolved defensive structures or chemical deterrents against predators. These interactions marked the beginning of ecological balance, where the success of one species depended on the adaptation of another. The world had entered an era of biological creativity, a slow explosion that would culminate millions of years later in the Cambrian diversification. The climate of this renewed Earth was relatively mild, but not without fluctuations. The cycles of glaciation had not ended entirely. Smaller ice ages would still come and go, yet none would match the scale of the Cryogenian. The planet's new atmospheric composition and continental arrangement prevented another full freeze. The feedback systems of carbon, water and life had become more resilient. The Earth had learned through catastrophe how to maintain equilibrium. The oceans of the post-glacial world must have been a place of wonder. The water, clearer than before, allowed light to penetrate to greater depths. Beneath the surface, colonies of algae formed vast meadows that rippled with currents. Floating plankton bloomed and faded in cycles that followed the seasons. The deep sea remained darker and quieter, but even there life spread. The microbial ecosystems that had once clung to vents now expanded across the seafloor, sustained by the rain of organic material from above. On the continents, life was still confined to microbial films. The air was oxygen-rich enough to support metabolism, but the surface was harsh, dry, hot during the day, and cold at night. Yet even here, the first steps toward colonization had begun. Cyanobacteria and lichens formed crusts on rock, stabilizing soil, and beginning the slow process of creating environments that could one day support plants. These pioneers were the architects of the land biosphere to come. Their presence marked the beginning of a long transition that would eventually bring the colour green to the continents. The interaction between these early terrestrial organisms and the atmosphere created subtle changes in climate regulation. As they trapped dust and moisture, they influenced how sunlight was absorbed and reflected. Over time, they contributed to the build-up of organic carbon in soils, further stabilising the carbon cycle. The garden that followed the ice was not limited to the seas. It was beginning to spread across the continents, molecule by molecule, layer by layer. The transformation of the Earth after the ice was both chemical and biological, but it was also aesthetic. The contrast between the frozen past and the living present was absolute. Where there had been silence, there was movement. Where there had been uniformity, there was diversity. The planet was regaining its complexity. Each cycle of growth, decay, and renewal added texture to the world. Sediments layered with life, air filled with the byproducts of metabolism, and seas that shimmered with organisms too small to see yet essential to everything that would follow. This flourishing was not only a recovery but a preparation. The conditions created by the post-Cryogenian world laid the groundwork for the next great leap in evolution, the rise of animal life as we know it. The oxygen-rich atmosphere, the nutrient-laden seas, and the stable climate formed a stage on which the Cambrian explosion would unfold. The garden was not yet filled with flowers or forests, but it held the seeds of both. The planet had gone from a mirror of ice to a canvas of possibility. Every rock, every droplet of water, every grain of sediment carried the memory of the world that had come before. The ice had erased much, but it had also renewed everything it touched. The scars of glaciers became valleys where rivers flowed. The minerals released by erosion fed the oceans. The gases exhaled by volcanoes became the air of the new world. It was as if the planet had been remade, its old systems reset, its potential restored. And through this rebirth, life continued to spread and adapt. The once frozen ocean now pulsed with energy. The surface shimmered with the colour of new growth. The air vibrated with the quiet hum of chemistry in motion. The world had transformed from desolation to abundance, from silence to song, and in doing so, it had set in motion everything that would follow. The rise of animals, the greening of the land, and the endless evolution of life that would one day lead to us. The garden was still young, fragile and full of change. The Earth had awakened from its icy sleep, but its story was only just beginning to unfold under the warmth of the returning sun, carried forward by the chemistry of life and the endless patience of time. Even after the warmth returned, the planet never truly forgot what had happened. The memory of frost was etched into its stones, buried in its sediments, and written in the chemistry of its air and water. Every mountain carried traces of the glaciers that had once covered it. Every continent bore the scars of ice, grooves cut deep into the rock where the frozen sheets had ground their slow path toward the sea. The Earth, though alive again, still carried the imprint of the cold that had once silenced it. The end of the Great Glaciation was not the end of its influence. The physical and chemical aftermath of the Cryogenian shaped the world that followed for hundreds of millions of years. As the ice retreated, it left behind landscapes stripped bare, exposing minerals that had not seen sunlight since the continents formed. The wind carried fine glacial dust across the surface, spreading it into the oceans, where it acted as fertilizer for the microbial blooms that followed the thaw. The planet's recovery was driven not only by warmth, but by the remnants of the cold itself. The rocks left behind by the glaciers told the story in detail. Beneath layers of carbonate formed after the thaw, geologists have found deposits of tillite, coarse sediments of mixed stones, gravel, and silt dropped by melting ice. Embedded in these layers are drop stones, large rocks that were carried by floating ice and released into soft marine mud as the icebergs melted. These stones, now found in regions that were once near the equator, remain one of the most compelling pieces of evidence that the ice had reached nearly every part of the globe. They are fossils not of life, but of climate, preserving the moment when the planet stood at the edge of habitability. The chemical record in those same rocks speaks of extremes. Isotopic anomalies in carbon and oxygen tell of drastic changes in temperature and in the cycling of gases through the atmosphere and ocean. Just before the formation of the cap carbonates, carbon isotope ratios plummet, suggesting a collapse of biological productivity during the deep freeze. Then, immediately after, they spike upward, recording the explosion of life that followed the thaw. The rock record is, in this way, a biological pulse, a heartbeat that stopped and started again. Even the air retained the imprint of the frost. Trapped bubbles in ancient glacial ice, though rare and fragile, show the composition of the atmosphere as it shifted from near collapse to renewal. During the coldest intervals, carbon dioxide levels were far higher than before the freeze, built up by volcanic emissions unable to be absorbed by the frozen seas. Methane, once abundant, declined as oxygen increased, its chemical fingerprints erased by oxidation. These transitions left long-term effects on climate stability, influencing how the Earth would respond to future changes. The physical shaping of the land was profound. Glaciers, with their immense weight, had pressed the continents downward. When they melted, the crust rebounded slowly, rising over thousands of years. This rebound altered drainage patterns, creating new river systems and basins. The sediment carried by these rivers built new coastal plains and deltas, forming environments that would later host rich marine ecosystems. The redistribution of water also changed the balance of weight across the planet, subtly affecting tectonic stresses and perhaps even influencing volcanic activity for millions of years afterward. In this way, the memory of frost was not simply a record of the past, but a continuing influence on the planet's dynamics. The erosion caused by ice had ground vast amounts of rock into fine material that fed the carbon cycle long after the glaciers vanished. The chemical weathering of this material drew carbon dioxide from the atmosphere, helping to moderate the extreme warmth that followed the thaw. It was as if the planet, having overheated and frozen in succession, was teaching itself how to balance its own systems. For life, too, the frost left a legacy. The genetic lineages that survived it carried with them the adaptations that had made survival possible: resistance to cold, the ability to form protective cysts, tolerance for low oxygen and high salinity. These traits, once essential for endurance, became the foundation for future diversity. Organisms that had learned to cooperate during scarcity retained those abilities, allowing the development of multicellular forms. The stress of the Ice Age had acted as a crucible, refining life's resilience and creativity. The ecosystems that arose after the thaw still bore traces of that evolutionary bottleneck. Genetic evidence suggests that many modern groups of microorganisms share ancestors that lived through the Cryogenian. These lineages show signs of population contraction followed by rapid expansion, a signature of survival through extreme hardship followed by proliferation in better conditions. The memory of frost was written not only in stone but in DNA, carried silently through time in the molecular machinery of every living cell. The climate, even in recovery, remained haunted by the mechanisms that had once driven it to extremes. The balance between greenhouse gases and reflectivity continued to fluctuate. Smaller ice ages came and went, though none reached the magnitude of the Cryogenian. The same feedback loop still operated: ice reflecting sunlight, carbon dioxide trapping heat. But the planet's new configuration of continents and atmosphere kept them within manageable bounds. The Earth had learned moderation, but it had not forgotten instability. In the oceans, the chemistry of the deep retained signs of the freeze long after the surface had warmed. Layers of sediment from the post-glacial period contained bands rich in iron and manganese, evidence of redox reactions as oxygen returned to the water. The reintroduction of oxygen into the deep sea was not immediate. It spread slowly, driven by the mixing of currents and the biological pump. Even as life flourished near the surface, the deep remained a record of what had been, quiet, dark, and chemically marked by the years of isolation. The volcanic activity that had ended the Snowball state also left a lasting imprint. The massive release of gases and minerals altered the isotopic composition of the Earth's crust. The sulfur isotopes in particular show distinct anomalies during and after the Cryogenian, indicating widespread volcanic emissions and atmospheric reactions under unique conditions. These chemical fingerprints serve as timestamps in the geological record, linking distant rock formations into a coherent timeline of the planet's recovery. Over millions of years, the scars of the ice softened, but they never disappeared. The valleys carved by glaciers filled with rivers and lakes, the smooth, polished rock surfaces weathered into soil. The sediments laid down by meltwater solidified into layers of stone that would, much later, form mountains themselves. Every landscape that came after was built upon the foundation left by the frozen world. The memory of frost became part of the architecture of Earth itself. As the planet stabilized, the influence of the Cryogenian extended beyond geology and biology. It became a pattern for planetary resilience. The same processes that had nearly destroyed life ensured its survival. The drawdown of carbon dioxide by weathering, the regulation of temperature through feedback loops, the persistence of volcanic outgassing, and the adaptability of life all demonstrated the interconnectedness of Earth's systems. The planet had proven that it could recover from catastrophe, not by avoiding change but by embracing it through cycles of balance and correction. In the time that followed, the world grew even more diverse. The Ediacaran organisms that appeared in the aftermath of the Ice Age were soon joined by new forms of multicellular life. The oceans filled with soft-bodied creatures, each exploring new strategies for survival: filter feeding, mobility, symbiosis. These early experiments in complexity were possible only because of the conditions created by the thaw. The oxygen levels established after the Snowball event provided the metabolic capacity needed for energy-intensive forms of life. Without the memory of frost, without the purification of the atmosphere, the release of nutrients, the stabilization of the climate, this next stage of evolution might never have occurred. The Cryogenian also changed the way continents interacted with climate. The breakup and rearrangement of landmasses during and after the freeze altered ocean currents, which in turn influenced global weather patterns. The placement of continents near the equator, which had once contributed to the runaway cooling, now helped maintain warmth by absorbing sunlight. The feedback systems that once trapped the planet in ice were replaced by ones that encouraged stability. The very factors that had caused catastrophe became safeguards against its return. Yet traces of that old vulnerability still lingered. The ice caps at the poles, smaller but persistent, remained as reminders of what could happen if balance were lost again. They were relics of a time when ice ruled the Earth, and their growth and retreat in subsequent ages would continue to shape sea levels, weather, and life itself. The Cryogenian had made ice a permanent character in Earth's story. Not the dominant force it once was, but a recurring one, tied to the rhythm of the planet's breath. Even now, hundreds of millions of years later, the memory of frost continues to influence how Earth behaves. The mechanisms that regulate carbon and temperature still follow patterns established in that distant past. The slow cycling of carbon between rock, ocean and atmosphere remains the planet's most important stabilizing system. When modern scientists study climate change, they are in part studying echoes of the same processes that froze and thawed the world long ago. The story of the Snowball Earth is ultimately a story about endurance, not only of life but of the planet itself. The Ice Age did not end the Earth's vitality, it deepened it. It tested the boundaries of habitability and revealed the resilience built into the system. The rocks that record its passage do not tell of failure but of recovery. Each glacial groove, each layer of tillite, each isotopic shift is a record of persistence. The memory of frost is the memory of survival. When modern glaciers creak and flow, carving valleys through stone, they echo that ancient event. When the polar ice reflects sunlight into space, moderating the climate, it repeats a process that once determined the fate of the entire planet. The same feedback loops that once plunged the world into silence now help maintain the conditions under which life thrives. The Earth remembers, not consciously, but through the physics and chemistry of its being. Every snowfall, every ice cap, every seasonal freeze is a faint repetition of that vast, transformative age. In the quiet layers of rock beneath our feet, the evidence remains. Geologists who split open ancient stones find within them the record of a frozen Earth. Polished grains of quartz, pebbles carried by glaciers, chemical signatures of ancient seas. These fragments are the planet's memory, each one a frozen word in a story written across billions of years. The frost is gone, but its lessons endure, that balance is fragile, that life is tenacious, and that even in the most complete stillness, the machinery of renewal continues to turn. And so the Earth, warmed and alive, still carries that quiet remembrance beneath its surface. Every gust of polar wind, every patch of sea ice, every glacial valley and mountain lake is a trace of that ancient memory. A reminder that the planet has been both more fragile and more resilient than we often imagine. The frost that once covered it completely has become part of its soul, preserved not only in stone and water, but in the deep rhythm of the Earth itself, where the past never truly disappears and the memory of cold still whispers beneath the warmth. The traces of that ancient freeze are not confined to the rocks. They persist in the atmosphere, in the rhythm of the oceans, in the very way the planet manages its own temperature. The Earth never truly lost the mechanisms that once plunged it into ice. It learned to live with them. Every winter that spreads frost across the continents, every sheet of ice that grows and recedes at the poles, is a subdued echo of the Cryogenian's long dominion. The memory of those ages is not a story locked in the past. It is active still, shaping the climate we live within now. The balance between sunlight, greenhouse gases, and reflectivity, the same triad that governed the Snowball Earth, continues to define our world. The feedback loops that once froze the planet still operate, though now within gentler limits. When ice expands, it reflects sunlight and cools the surface. When it melts, the darker land and ocean beneath absorb more heat, accelerating the warming. This dance between ice and energy is the foundation of every climate shift since the Cryogenian. The Earth's ability to regulate itself depends on the delicate interplay of these opposing forces. At the heart of this system lies the carbon cycle, the slow exchange of carbon between the atmosphere, the oceans, the biosphere, and the rocks below. During the Snowball era, this cycle was interrupted. With the surface sealed under ice, the usual process of removing carbon dioxide through rainfall and rock weathering stopped, allowing volcanic emissions to build up. When the ice melted, those same processes restarted with overwhelming force, drawing carbon from the air and stabilizing the climate. That cycle, a planet breathing in and out over millions of years, still operates today. It is the long-term thermostat that keeps Earth habitable, though it responds too slowly to correct the rapid changes humans now impose upon it. In today's world, we can still see the faint imprint of those ancient feedbacks. Polar regions act as mirrors, just as they did before. The Arctic and Antarctic reflect sunlight back into space, moderating global temperatures. Yet as the climate warms and ice retreats, the same positive feedback that once froze the world now works in reverse, amplifying the heat. The bright surfaces diminish, the dark ocean absorbs more sunlight, and the process accelerates. It is a smaller, faster echo of the same physics that once covered the equator in ice. The cryosphere, the collective system of Earth's ice, snow and permafrost, functions as both a relic and a regulator. It stores vast amounts of water, influences sea level, and stabilizes global temperatures. When the cryosphere changes, it sends ripples through every other part of the planet's system. During the Cryogenian, those ripples became waves that engulfed the entire world. Today, the same principles still apply, though the timescales have compressed. What once took millions of years now unfolds within centuries. The Earth's memory of ice is being tested in real time. The oceans, too, still bear traces of their ancient role. They remain the great reservoir of heat and carbon, absorbing energy and gases that the atmosphere cannot hold. Their circulation patterns, currents driven by temperature, salinity and wind, distribute warmth and regulate climate across the globe. When those patterns change, so does the planet's stability. The global conveyor belt of ocean circulation, which transports heat from equator to pole and returns cold water to the depths, is a descendant of the same system that once failed during the Snowball Earth, when ice choked the surface and halted exchange. The modern ocean is still vulnerable to disruptions in salinity and temperature, much as it was in that ancient time. In the high latitudes of the North Atlantic, for instance, melting ice and increased fresh water input from Greenland threaten to slow the overturning circulation that carries heat northward. If that process weakens, it could cool regions around the North Atlantic while warming continues elsewhere, altering weather patterns across the world. It is a smaller version of the same kind of instability that once tipped the planet into global ice. The mechanisms are the same, only the magnitude differs. Geological memory is not easily erased. The continents, shaped by glaciation and rebound, still affect how heat and moisture move around the globe. The mountain ranges formed or exposed after the Cryogenian continue to influence wind patterns and rainfall. The erosion of rock still draws down carbon dioxide, albeit slowly. These processes act as long-term stabilizers, countering excess heat over millions of years, but they are slow guardians, and the changes of the modern age happen too quickly for them to respond in kind. In the ancient world, volcanoes were the saviours of a frozen planet. Their emissions restored greenhouse gases to the atmosphere, ending the long winter. In today's world, the balance is reversed. Human industry releases carbon dioxide at a rate that dwarfs all but the most violent volcanic epochs. What once took nature millions of years, our species can accomplish in mere decades. The difference is not in mechanism but in speed. The physics of greenhouse warming has not changed since the Cryogenian. Only the scale and pace have. The concept of feedback remains central. Ice reflects sunlight, greenhouse gases trap heat, and temperature governs both. In the Cryogenian, That feedback drove the world toward cold. In our time, it drives it toward heat. Both directions stem from the same sensitivity, the planet's responsiveness to small changes in energy balance. This responsiveness is what makes Earth habitable, but it also makes it vulnerable. The same precision that allows stability over eons can produce instability when disturbed too quickly. Scientists studying modern climate draw on the lessons of the Snowball Earth to understand how runaway processes begin and end. The Cryogenian provides a natural experiment in planetary extremes. It shows that feedback loops can drive enormous transformations, but also that recovery is possible when stabilizing processes reassert themselves. Yet the timescales are starkly different. The warming that ended the snowball state unfolded over millions of years. Today's warming is measured in centuries. The planet can adapt, but life, especially complex life, experiences that adaptation as crisis. The ice that remains at the poles functions as a living memory of those older worlds. Cores drilled deep into Antarctic and Greenland ice preserve layers of snow stretching back hundreds of thousands of years, each layer recording temperature, composition, and atmosphere. Within them are traces of carbon dioxide, methane, dust, and isotopes that reveal the pulse of Earth's climate through time. These records show periodic swings, ice ages and warm intervals, echoing the grander cycles of the distant past. They are reminders that Earth's climate has always been dynamic, but also that it has limits beyond which balance fails. The role of oceans in regulating modern climate mirrors their ancient counterpart. They absorb roughly a quarter of the carbon dioxide released into the atmosphere each year, delaying but not preventing warming. In doing so, they become more acidic, affecting the shells and skeletons of marine organisms. This acidification parallels the chemical changes that occurred when the Cryogenian oceans first absorbed volcanic gases after the thaw. The same chemistry that once triggered rapid deposition of carbonates now threatens the stability of coral reefs and plankton. History is not repeating itself exactly, but the echoes are clear in the patterns. Clouds, too, retain their role as mediators of sunlight. In the frozen world, thin, high clouds of ice crystals reflected and scattered light, keeping the planet cold. Today, the balance between reflective and heat-trapping clouds determines much of the uncertainty in climate predictions. Their behaviour, how they form, where they drift, and what kind of light they let through, remains one of the great variables in Earth's thermostat. The mechanisms that once contributed to global freeze still govern the subtler fluctuations of the modern sky. The geography of the continents affects the planet's temperature just as it did in the Cryogenian. When large land masses sit near the poles, they encourage ice formation. When they cluster near the equator, they affect heat absorption and rainfall. During the Cryogenian, the arrangement of Rodinia helped trigger the global freeze by placing reflective land near the tropics. Today, though the continents are differently arranged, their influence remains. The distribution of land and ocean affects monsoon cycles, wind circulation, and the storage of heat. The physical shape of the world continues to act as a framework for its climate, just as it has for billions of years. Even the chemistry of weathering, the quiet process of rain reacting with rock, carries the Cryogenian's imprint. It remains one of the most important natural regulators of carbon dioxide. The rate at which silicate rocks erode determines how much carbon is drawn out of the atmosphere and locked away in minerals. During the Snowball Earth, this process stopped entirely under the ice, allowing greenhouse gases to accumulate. Today, human emissions far outpace the ability of weathering to counteract them, overwhelming the same system that once restored the planet. The ancient balance still operates, but too slowly to keep up with the speed of change. The polar regions act as our most immediate reminders of what happened when ice ruled the world. As they warm, meltwater flows into the oceans, raising sea levels and altering salinity. These shifts influence currents and weather far beyond the poles, just as the spread of ice once did. scientists studying modern glaciation see not only environmental change, but also planetary memory in motion, the reactivation of processes that defined Earth's deepest cold. The glaciers are withdrawing, but the principles remain the same: reflectivity, feedback, and the coupling of air and water in a fragile balance. The rhythm of climate oscillation, the waxing and waning of ice ages, owes much to what was established during the Cryogenian. The cycles driven by the Earth's tilt, orbit, and rotation, known as Milankovitch cycles, still influence temperature and ice formation. These astronomical patterns, interacting with feedbacks between carbon dioxide and albedo, have produced the repeating ice ages of the last few million years. Each of these smaller freezes is, in its own way, a faint echo of the Great Snowball, a reflection of the same underlying sensitivity to sunlight and carbon. The concept of a tipping point, often used in modern discussions of climate, is rooted in the understanding of how the Snowball Earth began. The idea that small, cumulative changes can cross a threshold and produce a runaway effect comes directly from the study of the Cryogenian. The planet's freeze was not caused by a single event, but by a slow accumulation of feedbacks that reached a point of no return. That knowledge shapes how scientists think about today's warming, that beyond certain thresholds, the collapse of ice sheets, the release of methane from permafrost, the death of forests, change may accelerate beyond control. The parallels extend beyond physics into the resilience of life itself. The organisms that survived the Snowball Earth did so by adapting to extremes, by enduring darkness, scarcity, and chemical change. The modern biosphere faces similar challenges in different forms. Species adapt or migrate as the climate shifts, while others vanish. The same pattern of contraction and renewal that followed the Cryogenian may play out again, though on a smaller scale and over a shorter time. The planet will persist. The question is how much of its present diversity will follow it into the next equilibrium. The Cryogenian offers perspective, not prophecy. It shows that Earth systems are capable of vast transformation and recovery, but only on timescales that dwarf human history. The processes that rescued the frozen planet, volcanic emissions, weathering, and biological feedbacks, operated over millions of years. The changes unfolding today occur within decades. The lessons of that ancient world are less about what will happen, and more about how the planet responds when pushed too far. It tells us that extremes are possible, that recovery is slow, and that the boundaries of stability can be crossed if feedbacks compound unchecked. In studying those echoes, scientists find both caution and continuity. The Earth is not fragile in the sense of being easily destroyed, but it is sensitive. Its balance depends on relationships between elements, ice and light, rock and air, water and heat, that are exact yet dynamic. When those relationships shift too quickly, the system finds a new equilibrium, but not always one friendly to complex life. The Snowball Earth stands as proof that the planet can survive nearly anything, but also that survival and habitability are not the same. The air we breathe carries atoms that once cycled through the oceans of that frozen time. The rocks beneath us were sculpted by ice that once reached the equator. The chemistry of the seas still bears the ratios established when the world thawed. These are not metaphors but continuities, tangible, measurable links between our present climate and the one that nearly ended all life. Every carbon atom in the air, every molecule of water in the sea has been part of this long conversation between heat and cold, light and reflection. When we look at the poles today, at the cracking shelves of Antarctica, at the thinning sea ice of the Arctic, we're seeing the same feedback loops in motion that shaped the Cryogenian. The difference lies only in cause and speed. The ancient freeze was triggered by the slow drawdown of carbon and the configuration of continents. The modern warming is driven by human industry, releasing carbon faster than any volcano ever could. Yet the physics of what follows is identical. The mirrors of ice are fading, and the dark water beneath them waits to absorb the sun. And still, the the planet remembers how to balance itself, even if the time it needs to do so exceeds our own. The feedbacks that froze and thawed it are still there, patient and indifferent. The Earth carries its past not as a burden, but as a rhythm, a set of responses refined over billions of years. The echoes of frost within today's warming world remind us that our climate is not separate from that ancient one. It is a continuation of the same long dialogue between light, air, and life. The pattern has not vanished. It has only changed its tempo. The world we know now carries warmth that once seemed impossible. Oceans move freely beneath a sky that changes by the hour. Ice retreats to the poles and mountains, where it gleams faintly beneath the sun, a remnant of an age when it ruled everything. Wind moves through forests that did not yet exist when the planet lay frozen, and rivers carve paths through valleys once filled with glaciers. The Earth, for all its calm, still breathes with the slow rhythm it learned in that deep frozen silence. It has thawed, yet it remembers. If one could stand, even for a moment, at the edge of that ancient world just as it began to melt, the sight would have been both beautiful and terrifying. Great sheets of ice cracked like thunder as the first warmth seeped in. Water pooled in vast basins, reflecting a pale sun that seemed to tremble in the mist. Steam rose where lava met the cold, curling into clouds that caught the weak light and scattered it into colour. Each sound, the slow rush of melting, the creak of shifting glaciers, the muffled rumble of distant volcanoes, would have been new to a planet that had forgotten what noise was. For millions of years there had been no sound but the whisper of wind over ice. The first trickles of water broke that silence. Those first rivers ran across landscapes untouched by erosion, carving grooves into rock that had lain beneath the ice for ages. The air was thick and heavy with carbon dioxide. The rain fell warm, washing minerals from the land into the sea. The smell of the world would have been sharp, almost metallic, volcanic gases mingling with the scent of wet stone. The oceans were darker then, filled with sediments and nutrients, but beneath their surface life was already stirring. The ice had never managed to kill it. It had only hidden it away until the time was right. When light returned to the water, photosynthesis bloomed again, and with it came colour. The seas shimmered green where algae spread, and blue where sunlight reached deeper currents. The cycle of life resumed quietly, without fanfare, as if it had only been sleeping. The microorganisms that had waited beneath the ice began to multiply, feeding on minerals carried down by the melting glaciers. Their byproducts changed the chemistry of the water, producing oxygen that slowly filled the atmosphere once more. The frost had ended, but its legacy had only just begun. The years that followed were not calm. The thaw brought chaos. The greenhouse gases that had saved the planet from its frozen state made it nearly overheat. Rain fell in endless torrents. Rivers swelled into inland seas. The air shimmered with heat during the day and steamed at night. It was an age of transformation, violent, unsteady, and necessary. The Earth had to pass through this turbulence to find balance again. Out of that instability came renewal. Over time, the temperatures stabilized. The clouds thinned. The oceans cleared. Oxygen built up in the air, and the sky deepened from its pale haze into a true blue. Volcanoes continued to erupt, but their ash now mixed with moisture to form fertile soils. The continents began to host the first ecosystems since the ice had vanished. They were simple, mats of cyanobacteria and algae coating rocks near the shore, but they were the foundation upon which all future life would rise. In these moments of rebirth, the Earth was both young and old. The scars of the glaciers remained visible, etched into the land as though the planet wanted to remember. The mountains were worn smooth. The valleys were broad and U-shaped. The basins filled with lakes that gleamed under the recovering sun. Each geological feature was a trace of pressure and cold, preserved long after the ice itself had gone. Even now, those same forms can be seen in rocks across every continent, silent witnesses to the world's long sleep. The balance between warmth and cold became the planet's heartbeat. The ice never vanished completely. It retreated to the poles, where it lingered as a reminder of what once was. Its reflection cooled the air, its melt fed the oceans, and its presence shaped the winds that would define future climates. The Earth had learned to keep a piece of its cold heart safe, to remember what unchecked feedback could do. The polar caps became the quiet anchors of the planet's stability, regulating temperature through their ability to mirror the sun's light back into space. They were remnants of catastrophe turned into instruments of balance. The cryosphere, the frozen part of the Earth, became a kind of planetary memory. Each snowfall and glacier built upon the story of the past, layering history in ice that, one day, others would drill through to read. Within those layers lie the particles of volcanic ash, traces of ancient air, and the faint chemical fingerprints of the gases that once remade the world. The ice remembers every change, every pulse of warmth and cold, storing the history of climate in silence. Long after the Cryogenian, smaller ice ages would come. The planet would cool again and again, though never as completely. These cycles, driven by the tilt of the Earth and the slow movement of continents, repeated the lessons of the ancient freeze in miniature. Each one brought reflection, adaptation, and balance. Life endured through them all. By then the world was richer, oceans filled with animals, continents covered in vegetation. The frost was no longer a sentence, it was a rhythm. The planet had learned to breathe between extremes. When we look at the modern Earth, what we see is the result of that long, repeating dialogue between warmth and cold. The continents are shaped by ice and erosion. The chemistry of the air is maintained by processes born from the thaw. The diversity of life owes its existence to the resilience learned during those frozen ages. Even our capacity to understand the climate, to measure it, predict it, and affect it, comes from the geological record of those ancient events. Every graph of temperature, every model of feedback, every study of carbon began with what the rocks and ice of the Cryogenian revealed. In that sense, the frozen world never really ended. It continues to influence how we live and how we think. The very concept of planetary balance, that a world can shift between extremes and still recover, is something we learned from those deep ages. The Earth was not fragile, but it was precise. Small changes led to vast transformations, yet through each one, life persisted. The same feedbacks that once threatened to extinguish it eventually created the conditions for its expansion. The ice had taught the world to adapt. If one were to wander across a modern glacier, with the wind biting through the air and the sound of cracking ice echoing across a valley, it would not be hard to feel that connection. The cold underfoot is the same cold that once reached the equator. The frozen air carries the same chemistry, the same crystalline structures, the same slow patience. The patterns of fracture in the ice mimic those that once covered continents. The processes that move glaciers today, their slow creep, their grinding against stone, are the same that carved the ancient world. The difference is only in scale. The memory of frost is alive in every winter storm, every snow-covered peak, every frozen sea. Modern ice behaves like an archive. In Antarctica and Greenland, cores drilled deep into the ice reveal layers that stretch back hundreds of thousands of years. Each layer holds a record of snowfall, dust, and trapped air. The gases within these bubbles are time capsules, samples of the atmosphere as it was long before human memory. They show the rise and fall of carbon dioxide, the rhythm of glacial cycles, the slow dance of temperature and chemistry that defines climate. Within those records are faint echoes of processes that began during the Cryogenian. The slow build-up of greenhouse gases, the reflection of light by ice, the interplay of feedbacks, all are written there in molecular detail. When the ice sheets retreat, as they are doing now, they do not simply vanish. They release the water that once bound them, altering coastlines and ocean currents. They expose rock that has not seen daylight for thousands of years. They change the albedo of the planet, just as they did when the first glacial periods ended. The same chain of cause and effect continues, though now accelerated by the speed of human activity. The Earth responds as it always has, by adjusting, by finding a new equilibrium, even if the transition is turbulent. For scientists, the Cryogenian remains a lesson in thresholds. It teaches that small changes can lead to runaway effects, that feedbacks can amplify beyond control, and that recovery, while possible, is slow. It also teaches that life is resilient beyond expectation. The microorganisms that endured under ice paved the way for every organism that came after. Their survival in the cold and dark made possible the explosion of complexity that followed the thaw. The ice nearly ended life, but instead it refined it. The warm world that followed became the garden of the Ediacaran and the Cambrian, the seas where animals first appeared and evolved into countless forms. All of it, every coral reef, every forest, every living thing, emerged from the planet's ability to recover from cold. The frost had cleansed the Earth's systems, resetting the chemistry of the oceans, clearing the air and priming the environment for oxygen and growth. Without that long frozen pause, the planet might never have developed the diversity it now holds. The cycle of freezing and thawing also reshaped the way the Earth interacts with its star. The Snowball periods demonstrated the power of reflectivity, showing that sunlight alone is not enough to maintain warmth if it is reflected away. Since then, the planet has balanced between absorbing and reflecting energy, guided by clouds, ice and vegetation. Even today, when sunlight glints off the polar caps, that same dynamic continues. The light that leaves Earth, scattered into space, carries within it the physics of the Cryogenian, a whisper of that long-ago brightness when the world was white. To imagine the Earth then and now side by side is to see two halves of the same being. The frozen sphere and the living one are not opposites. They are phases of a single planet learning to keep itself in balance. The frost tested its resilience. The warmth revealed its creativity. The same geological and biological systems that nearly failed became the very ones that made recovery possible. The cycles of ice and heat have become part of the Earth's nature, embedded in every climate fluctuation, every shifting current, every gust of wind. The quiet understanding that comes from looking at that history is a kind of comfort. The Earth has survived worse than anything humans have yet brought upon it. It has frozen solid, boiled in volcanic haze and been struck by asteroids. Each time it recovered, though never exactly the same. The resilience of the planet lies not in preventing change but in transforming through it. The world is not static. It endures by evolving. At night, when the poles glow with auroras and the air freezes into crystals that catch the light, the Earth seems to remember its old state. There is a stillness in the cold that feels ancient, a kind of echo from the time when the entire planet looked like that. The same light that flickers above the polar skies once shimmered over a frozen equator. The same chemical reactions that create those colours began in the ancient atmosphere, shaped by the gases of volcanoes that melted the snowball world. The continuity is unbroken. The warmth that now spreads across the surface, in deserts, in forests, in oceans, is the latest expression of that balance. It is temporary as all climates are, but it is part of a continuum that stretches back through eons. The frost will return in time, in one form or another, just as the warmth did. The Earth's rhythm is not one of permanence but of alternation. Warmth follows cold, life follows dormancy, balance follows imbalance. Somewhere, deep beneath the Antarctic ice, microorganisms still live much as they did during the Cryogenian, feeding on minerals, breathing chemical gradients in the dark. Their existence is not a curiosity but a memory, the living continuation of that ancient adaptation. They persist where light does not reach, carrying within them the legacy of a time when all life did the same. When scientists sample these icy ecosystems, they are not merely studying modern extremophils, they are meeting the descendants of survivors from the world's greatest trial. If you could drift above the Earth at night looking down from the quiet of space, you would see a planet glowing faintly. Blue oceans, white caps, green continents under scattered clouds. It is warmer now, but not without the fingerprints of its frozen past. The continents it wears, the gases it breathes, the balance it maintains, all shaped by the frost that once covered it completely. The warmth that surrounds us is not separate from that cold. It is the consequence of it, the other half of the same story. And so the planet turns beneath a soft, stable sun, its warmth radiating outward, its poles glittering faintly, its memory intact. The same physics that froze it still governs its breath. The same chemistry that thawed it still feeds its air. The same light that once could not penetrate its shell now bathes it in gold. The Earth rests between its extremes, alive because of both. The frozen silence gave it strength. The returning warmth gave it colour. What remains is balance. A planet that remembers, a world that endures, turning quietly through the dark, carrying in its heart the memory of frost and the promise of warmth that always follows.